Close your eyes for a moment and picture the beginning of everything. Not the slow, gradual beginning you might imagine, but a violent, explosive birth, the Big Bang. A point of infinite density of all energy and space and time, suddenly roaring into existence. But what happened in the very first moments, in that fleeting, almost incomprehensible sliver of time right after the initial flash? There exists a period so brief, so bizarre, that it defies our everyday understanding of reality. This is the cosmic inflation era, a fraction of a second where the universe didn't just expand. It ballooned outward at a speed faster than light itself, stretching the very fabric of space in an explosive growth spurt that set the stage for every galaxy, every star, and every planet that would ever form. In less time than it takes to blink, the universe was fundamentally forged, and yet this incredible event left behind a trail of profound mysteries that challenge our deepest understanding of physics. Think about that for a second. The entire cosmos, everything we can observe and everything beyond our view, was shaped in an instant so fleeting we have no direct record of it. This era is the universe's own origin story, the crucial first chapter that determined its ultimate fate, and yet it remains shrouded in questions. How could something expand faster than light? What force could possibly be powerful enough to drive such an incredible acceleration? And perhaps most hauntingly, what clues did this inflationary period leave behind, hidden in the faint whisper of ancient light or the large-scale structure of the cosmos, waiting for us to decipher? We are left grappling with the echoes of that monumental event, trying to piece together a puzzle where half the pieces are missing, a testament to just how strange and wondrous our universe truly is. That's the journey we're embarking on today, a deep dive into one of the most exhilarating frontiers of modern cosmology. We're going to explore the 25 greatest mysteries born from that inflationary spark, from the nature of the mysterious inflated field that powered the expansion to the hunt for primordial gravitational waves, ripples in space-time itself from the universe's first moments. This isn't just a story about particles and equations. It's a human story of curiosity, of our relentless drive to understand our place in the cosmos. We'll uncover why these ancient questions matter today and how answering them could revolutionize our view of reality. So get comfortable, open your mind, and prepare to travel back to the very edge of time itself, to an era of unimaginable power and transformation that made our existence possible. So what was the catalyst that set off this incredible runaway expansion of the universe? This is our first great mystery, a question that strikes at the very heart of the cosmic inflation theory. We know that it happened, the observational evidence is compelling, but why it happened, what specific set of conditions flipped the switch, remains one of the most profound puzzles in all of science. The leading hypothesis points to a mysterious entity known as the inflated field. Think of this not as a field of grass, but as an invisible energy field that permeated all of space in that first fraction of a second. According to the theory, this field found itself in a peculiar state, a false vacuum. Imagine a ball resting precariously on the very peak of a steep hill. That position is unstable, full of potential energy, but it's not its true, stable state. The ball wants to roll down into the valley below. In the same way, the inflated field was trapped in a high-energy state, and the moment it began its inevitable roll down its energy landscape that released energy, an absolutely staggering amount of it, was converted into the fabric of spacetime itself, causing the universe to inflate at an exponential rate. This transformation, this release of pent-up potential, is what we believe ballooned a subatomic speck of space into a cosmos of astronomical proportions in an almost impossibly short time. However, calling this a field is a bit of a simplification that hides a mountain of complexity. We're not talking about a magnetic field or anything we can easily measure. This is a quantum field, a fundamental component of reality whose properties are entirely speculative. What were its characteristics? How did it interact with other fields? We simply don't know. Proving its existence is a monumental challenge because inflation, by its very nature, would have wiped the slate clean, erasing any direct evidence of what came before it. It's like trying to figure out what a snowball looked like by studying the puddle it melted into. The inflated field is a brilliant piece of theoretical physics, an elegant solution that fits our models beautifully, but it remains frustratingly beyond our experimental reach. This leads to other, even wilder possibilities. Could inflation have been triggered by a phase transition, similar to how liquid water abruptly freezes into ice? Or was it a consequence of the unification of the fundamental forces of nature, a moment when gravity, electromagnetism, and the nuclear forces were all one and the same? Some theories even suggest our universe is just one bubble in a vast, eternally inflating multiverse, where new bubbles are constantly being born from the inflationary background. The trigger, then, might not have been a unique event, but a common, ongoing process in a reality far grander than we can perceive. The hunt for the trigger forces us to confront the limits of our knowledge and our tools. We are peering back to a time when energy scales were so high that they dwarf anything our particle accelerators, like the Large Hadron Collider, can ever hope to recreate. We are essentially trying to decipher the very first law of the universe, the initial condition that set everything else in motion, with only the faintest of cosmic echoes to guide us. If the trigger for inflation is a deep puzzle, then the moment it stopped is just as baffling. We have this image of the universe expanding at an unbelievable rate, but then, just as suddenly as it began, this incredible growth spurt ceased. It didn't just slow down, it effectively came to a halt, making way for the more gradual, steady expansion of the classic Big Bang. So what caused the brakes to be applied? The prevailing idea is a process cosmologists call reheating. Remember that inflated field, the one that was rolling down its energy hill? Well, according to this theory, it didn't just roll to a stop at the bottom. Instead, as it reached the lowest point in its energy landscape, it began to oscillate rapidly, like a weight dangling from a spring that's been pulled and released. And with each one of these incredibly fast vibrations, the energy that was stored in the field itself began to decay, transforming violently and efficiently into a seething, hot bath of fundamental particles, quarks, electrons, photons, everything that would eventually build the atoms of our world. This was the moment the universe truly became hot, filling with the raw material for all future structure. This reheating process is what connects the ethereal, rapid expansion of inflation to the tangible, particle-filled universe we know emerged next. But this transition had to be exquisitely, almost unnervingly precise. If the inflated field had decayed just a little too quickly, the universe would have been reheated to a much lower temperature. The resulting cosmos would have been too cold and dilute for galaxies to ever coalesce. It would be a vast, dark, and empty void. On the other hand, if the decay had been slightly slower, the energy release would have been even more ferocious. The universe would have become far too hot and dense, causing matter to annihilate too rapidly or perhaps even collapse back on itself. In either of these scenarios, a universe capable of fostering life, or even complex structures like stars and planets, would never have arisen. The fact that we exist to ponder this question is a testament to a transition that was, for reasons we don't understand, perfectly tuned. This fine-tuning leads us into even more speculative territory. Was this perfect ending just an incredibly fortunate roll of the cosmic dice, a 1 in a trillion accident? Or does it point toward a deeper principle, a law of physics that naturally guides the inflated field to decay in this specific, life-allowing way? Some physicists propose that our universe is just one of countless others in a vast multiverse, each with its own rules and its own version of inflation. In most of these universes, the transition was messy and imperfect, leading to cosmic dead ends. We, of course, find ourselves in one of the rare bubbles where everything aligned perfectly, a concept known as the anthropic principle. It's a controversial idea, but it highlights the sheer improbability we're faced with. The mystery of how inflation ended is therefore inseparable from the mystery of why our universe is so hospitable. It forces us to ask whether the laws of physics as we know them are truly fundamental and universal, or if they are merely local bylaws in our particular cosmic neighborhood, the unique outcome of a graceful exit from an era of unimaginable expansion. But to truly confirm that inflation happened, we need more than just the afterglow of the Big Bang. We need to find a signal that came directly from the inflationary storm itself. This brings us to our third great mystery, the hunt for the primordial gravitational wave background. Imagine the fabric of space-time not as a static stage, but as a dynamic, fluid entity. Now picture the universe in its first fleeting moments, undergoing that violent, exponential stretching. Such a cataclysmic event wouldn't have been smooth. The incredibly rapid expansion would have sent powerful shockwaves, literal ripples, through the very foundation of spacetime itself. These are primordial gravitational waves, and they are the ultimate cosmic messenger from the inflation era. What makes these waves so special, and why are they considered the holy grail of inflation evidence? It's because they are a direct product of the expansion mechanism, completely unaffected by the messy particle interactions that came afterward. While the cosmic microwave background gives us a picture of the universe hundreds of thousands of years after the Big Bang, these gravitational waves would carry an untainted imprint from a time so early it's almost inconceivable. They are the universe's first vibrations, a fossil record etched not in matter or light, but in the geometry of reality. Detecting them would be like finding the original signature on the cosmic birth certificate. The most promising place to look for their faint signature is actually within the cosmic microwave background. The theory predicts that as these primordial gravitational waves traveled through the universe, they would have subtly polarized the light of the CMB in a very specific, swirling pattern known as B-mode polarization. It's a faint, twisted signature in the ancient light, a ghostly fingerprint left by the ripples of spacetime. Finding this specific pattern is the primary goal of several ambitious experiments, from highly sensitive telescopes at the South Pole like the BICEP array to future space-based observatories. A confirmed detection would be the smoking gun, the direct, incontrovertible proof that the cosmic inflation theory is correct. Yet, despite decades of searching, this definitive signal has remained elusive. The hunt is phenomenally difficult. The primordial gravitational wave background is incredibly faint, a whisper buried under a cacophony of other cosmic signals. One of the biggest challenges is foreground contamination, particularly from dust within our own Milky Way galaxy. This interstellar dust can also polarize light in ways that mimic the sought-after B-mode pattern, creating a convincing illusion that has led to premature announcements of discovery in the past. Teasing apart the true cosmological signal from this local galactic fog requires exquisite precision and multiple observations across different frequencies of light. The absence of a clear detection so far is itself profoundly interesting. It forces us to confront other possibilities. Perhaps the simplest models of inflation are wrong, and the inflationary energy was lower than we predicted, producing gravitational waves too weak for our current instruments to perceive. Or perhaps the process of reheating, the transition out of inflation, was much more complex and somehow suppressed the production of these waves. Their continued illusion pushes our experimental capabilities to the absolute limit and compels theorists to broaden their thinking, to explore more nuanced and varied models of how that initial explosive growth might have unfolded. The next generation of experiments, including space-based gravitational wave observatories, will listen for these ripples with unprecedented sensitivity. Whether they finally hear the faint echo of inflation or continue to find silence, the result will dramatically reshape our understanding of the universe's first and most dramatic moment. Now, let's turn our attention to a puzzle so fundamental it helped convince physicists that an idea as radical as inflation had to be true. It's called the horizon problem, and it asks a very simple question with a deeply unsettling answer. Why does the universe look the same in every direction? Specifically, when we look at the cosmic microwave background, that fossilized light from the early universe, we find that its temperature is incredibly uniform. No matter which patch of the sky we point our telescopes at, whether we look east, west, north, or south, we measure the exact same temperature to within a tiny, tiny fraction of a degree. This seems reasonable at first glance until you consider the speed limit of the universe, the speed of light. In the standard Big Bang model without inflation, there simply hasn't been enough time since the beginning of the universe for light or heat or any kind of information to travel from one distant horizon to the other to even out these temperatures. Imagine two people standing on opposite sides of a vast, cold field, each holding a cup of hot coffee. If they can't communicate or exchange heat in any way, it would be a miraculous coincidence for their coffee to cool to the exact same temperature at the exact same time. The universe presents us with this same miracle on a cosmic scale. Regions of the cosmos that are billions of light years apart today were, in the early universe, so far separated that not even a single photon could have crossed the gap between them in the entire history of the cosmos up to that point. They were forever beyond each other's horizon, completely causally disconnected, and yet they managed to coordinate their properties with perfect precision. How could this be? This is where cosmic inflation provides its most elegant and powerful solution. The theory proposes that these seemingly disconnected regions of space were not always strangers. In fact, in the first fleeting moments before inflation began, the entire observable universe was crammed into a volume vastly smaller than a single atom. It was a tiny, submicroscopic speck where every part was in intimate contact with every other part. This primordial nugget had more than enough time to reach a uniform temperature, to mix and mingle and smooth itself out into a perfectly balanced state, just like a well-stirred cup of coffee. Then inflation struck. That unimaginably rapid stretching of space-time didn't just make the universe large. It took those once connected regions and flung them apart at speeds far exceeding the speed of light. It's crucial to understand that this doesn't violate Einstein's relativity, which forbids objects from moving through space faster than light. Instead, inflation was the expansion of space itself, and there is no known speed limit on that. So, these regions, which were once neighbors, were suddenly separated by an immense and growing void. They were carried so far apart so quickly that they appear to us now as opposite horizons, forever out of touch. Their matching temperatures aren't a coincidence. They are a relic of a time when they were all part of the same tiny, cozy, well-thermalized neighborhood. Inflation provides the missing link, the shared history that explains the uniformity we observe. While the solution seems beautiful, it does open up a new layer of questions. The level of uniformity we see is almost too perfect. The temperature differences across the sky are less than 1 part in 100,000. For inflation to produce such a smooth result, the initial patch of space that inflated must have been extraordinarily homogeneous and isotropic to begin with. What physical process set up that pristine initial condition? Some physicists argue that inflation doesn't so much solve the horizon problem as it pushes it back one step further, exchanging the question of why is the large universe uniform? For why was the microscopic pre-inflationary universe uniform? Furthermore, the very mechanism that creates this stunning uniformity also has a fascinating side effect. According to quantum mechanics, empty space is never truly empty. It's a seething foam of virtual particles popping in and out of existence. During the inflationary expansion, these tiny quantum fluctuations in the inflated field itself were stretched to enormous astronomical sizes. These minute imperfections, these tiny wrinkles in the fabric of space-time, became the seeds for all the structure we see in the universe today. Every galaxy cluster, every swirling nebula, every single star owes its existence to a microscopic quantum jitter that was magnified by inflation. So, in a beautiful cosmic irony, the same process that made the universe incredibly smooth on the largest scales also planted the seeds of all its future lumpiness and structure. The horizon problem, therefore, is not just an isolated mystery. It's deeply intertwined with the very origin of galaxies and the nature of quantum reality, showing us how the largest structures in the cosmos are connected to the smallest possible fluctuations at the dawn of time. Another profound clue that points directly to an inflationary past is the overall shape of the universe itself. This is the flatness problem, and it deals with one of the most fundamental properties of our cosmos, its geometry. According to Einstein's theory of general relativity, the sheer amount of matter and energy in the universe dictates the curvature of space on the largest scales. Think of space not as an empty void, but as a dynamic fabric that can be bent and warped. This fabric can take on one of three possible geometries. It could be positively curved like the surface of a sphere where parallel lines eventually meet. It could be negatively curved like a saddle where parallel lines diverge. Or it could be perfectly flat like a sheet of paper where the rules of Euclidean geometry we learned in school hold true. Now, based on the density of all the energy and matter in the cosmos, there is a specific critical value that determines this fate. If the actual density is above this critical value, the universe is closed and spherical, destined to eventually collapse back on itself in a big crunch. If the density is below the critical value, the universe is open and saddle-shaped, destined to expand forever into a cold, dilute emptiness. But if the density is exactly at the critical value, the universe is flat and will keep expanding, but at a rate that slows towards zero over an infinite amount of time. This is where the mystery deepens. When we take the most precise measurements we have from the cosmic microwave background and large-scale galaxy surveys, we find that the observable universe is flat to an astonishing degree of precision. The actual density of the cosmos is so incredibly close to the critical density that any deviation is smaller than 1 part in a million. To appreciate how bizarre this is, imagine trying to balance a pencil perfectly on its tip. The slightest breath of air, the tiniest vibration, would send it tumbling over. Now, imagine that pencil has been balancing for billions of years. That's the level of fine-tuning we're talking about with the universe's density. In the standard Big Bang model, any small deviation from this perfect flatness would have been dramatically amplified over time. If the early universe had been even slightly more dense, it would have collapsed eons ago. If it had been even slightly less dense, it would have flown apart so rapidly that no galaxies or stars could ever have formed. The fact that we exist in a universe that is still expanding after nearly 14 billion years and yet is so perfectly balanced seems like an unbelievable coincidence. The odds of the universe naturally starting out with such a precise balance are astronomically low. Cosmic inflation provides a powerful and elegant resolution to this puzzle. The mechanism of exponential expansion acts like a cosmic iron, flattening the universe by stretching space itself to an incredible degree. Picture the surface of a crinkled, wrinkled prune. This represents the early universe, which could have had any arbitrary curvature. Now, imagine blowing that prune up to the size of the entire Earth. As it expands, the local bumps and curves become less and less significant relative to the vast scale. From the perspective of a tiny ant walking on its surface, the ground would appear perfectly flat. Inflation did exactly this to the fabric of space. By stretching a tiny, primordial patch of the universe by a factor of at least 10 to the power of 26 in a fraction of a second, It smoothed out any initial curvature to such an extent that the observable universe we inhabit today appears perfectly Euclidean. The reason the universe looks flat isn't because it was miraculously born that way. It's because the phenomenal stretching of inflation made it that way, regardless of its initial shape. This flattening process is a direct and robust prediction of inflationary theory, and the observational confirmation of a flat universe is one of the strongest pillars of evidence supporting it. However, this elegant solution also opens a door to one of the most mind-bending concepts in all of cosmology, the multiverse. If inflation can flatten our observable universe, what about the entire cosmos beyond what we can see? Many models of eternal inflation suggest that the process never truly stops everywhere. Instead, our universe might be just one bubble of stabilized space in a vast, eternally inflating meta-universe. In this grander picture, the overall geometry of the entire multiverse could be highly curved and complex, but each individual bubble, inflated to an enormous size, would appear flat to its own inhabitants. This leads to a profound shift in perspective. The apparent fine-tuning of our flat universe may not be a lucky accident at all, but simply a selection effect. In a multiverse containing countless bubble universes with all sorts of different geometries and physical laws, we obviously find ourselves in one of the rare, stable, flat bubbles that can support the formation of galaxies, stars, planets, and life. The flatness problem, therefore, transcends a simple question of geometry. It forces us to confront the ultimate nature of reality, asking whether our universe is a unique, finely tuned entity or merely one page in an infinite cosmic library. But this incredible smoothing effect of inflation creates another, even more fascinating puzzle. If the universe became so perfectly uniform, how did we end up with a cosmos filled with magnificent structures, galaxies, clusters, and the vast cosmic web? The answer lies in a beautiful marriage of the very large and the very small, a process where the ghostly rules of quantum mechanics were written across the sky. This is the origin of all structure, and it begins with a fundamental truth: perfect emptiness is impossible. Even in a complete vacuum at the tiniest scales, space is never still. It's a turbulent sea of energy where virtual particles and antiparticles constantly flicker in and out of existence. These are quantum fluctuations, momentary borrowings of energy that defy classical physics, and they were present even in the primordial inflated field that drove the universe's expansion. In that first fraction of a second, this field was not a perfectly smooth, placid lake. It was more like a choppy ocean on a microscopic scale, with tiny, random variations in its energy density happening everywhere all the time. Under normal circumstances, these fleeting jitters would have been utterly insignificant, appearing and vanishing far too quickly to have any lasting effect. But inflation created utterly abnormal circumstances. As space expanded at a dizzying, exponential rate, something remarkable happened to these quantum ripples. The fabric of space-time stretched so rapidly that it literally pulled these microscopic fluctuations apart, locking them in place and stretching their wavelengths to astronomical sizes. A quantum flicker that was once smaller than a subatomic particle in an instant became larger than a galaxy cluster. This process of freezing in is one of the most profound consequences of inflation. It took the random, unpredictable nature of the quantum world and imprinted it onto the geometry of the cosmos itself. The tiny overdensities and underdensities in the inflated field became permanent wrinkles in the fabric of spacetime, regions where the gravitational pull was ever so slightly stronger or weaker than the average. These frozen wrinkles became the cosmic seeds for everything that followed. After inflation ended and the universe reheated, filling with a hot, dense plasma, gravity went to work. Those regions that had a tiny bit more energy and mass from the original quantum fluctuation had a slightly stronger gravitational pull. Over hundreds of millions of years, this minute advantage allowed them to tug on the surrounding matter, gradually pulling in more and more gas and dark matter. The underdense regions, conversely, slowly emptied out. What began as quantum noise on a subatomic scale grew through gravitational instability into the first clumps of matter, which coalesced into stars, which gathered into galaxies, and which were themselves drawn together into the immense clusters and superclusters we observe today. The entire cosmic web, the vast, sponge-like structure of filaments and voids that defines the large-scale universe, is a direct magnified trace of those initial quantum jitters. Every galaxy, including our own Milky Way, can trace its ultimate origin back to a specific patch of space where, during inflation, a random quantum fluctuation created a spot that was just a little bit denser than the space around it. This insight provides an incredibly powerful link between two theories that are otherwise notoriously difficult to reconcile: the quantum physics of the incredibly small and the general relativity that governs the universe at its largest scales. Inflation acts as the bridge, using the expansion of space itself to translate quantum behavior into gravitational initial conditions. This theory doesn't just offer a compelling story. It makes precise, testable predictions about the patterns we should see imprinted on the oldest light in the universe, the cosmic microwave background. The CMB is often called a baby picture of the cosmos, and it's here that the fingerprints of those stretched quantum fluctuations are most clearly visible. The temperature of this ancient radiation is not perfectly uniform. It shows tiny variations, anisotropies, of about 1 part in 100,000. These hot and cold spots correspond directly to the density fluctuations seeded by inflation. The specific statistical properties of these spots are a direct reflection of the nature of the quantum fluctuations that produced them. Inflation predicts that these primordial seeds should have two key characteristics. First, they should be scale invariant, meaning that the relative magnitude of the fluctuations is roughly the same across all different size scales, from the size of a galaxy to the size of the observable universe. This is a hallmark of the rapid, exponential expansion that inflation provides. Second, and perhaps even more telling, the fluctuations should be Gaussian and adiabatic. Gaussian means they are fundamentally random, with no preferred pattern or correlation between different fluctuations, exactly what you would expect from a quantum mechanical origin. Adiabatic means that the fluctuations affected all types of matter and energy in the same way. The number of photons, baryons, and dark matter particles all went up and down together in these overdense and underdense regions. When we point our most powerful telescopes, like the Planck satellite, at the CMB, this is exactly what we see. The observed pattern of hot and cold spots matches the predictions of inflationary theory with stunning accuracy. The statistical distribution, the scale invariance, and the adiabatic nature of the fluctuations all line up with the idea that they were born from quantum vibrations stretched across the cosmos. It is a triumphant confirmation of a deep theoretical insight, showing that the blueprint for the entire visible universe was drawn by quantum mechanics in its first moment of existence. While inflation elegantly explains the smoothness and structure of our universe, it also resolves a more obscure but equally critical puzzle, one involving hypothetical relics that should be everywhere yet are nowhere to be found. This is the mystery of the missing magnetic monopoles. To understand why their absence is so puzzling, we need to revisit the concept of symmetry breaking in the very early universe. In our current understanding, magnets always come with two poles, a north and a south. You can break a bar magnet in half, but you don't get isolated poles. You just get two smaller magnets, each with its own north and south. A magnetic monopole, however, is a hypothetical particle that carries only one magnetic charge, either a solitary north or a solitary south pole. Their existence isn't just a whimsical idea. They are a robust prediction of grand unified theories, which propose that the electromagnetic, weak, and strong nuclear forces were once a single, unified force in the extreme heat of the early cosmos. As the universe expanded and cooled, it underwent a series of phase transitions, much like steam condensing into water or water freezing into ice. During one of these transitions, as the unified force split into the distinct forces we see today, the physics suggests that topological defects should have formed in the fabric of spacetime. Think of it like the cracks and fissures that form in ice as it freezes. Magnetic monopoles are one such type of cosmic crack, stable, incredibly massive particles that would have been produced in staggering numbers. In fact, theoretical calculations suggest they should have been as common as protons, meaning there should be at least one monopole in every nucleus of every atom in the universe. Their density should be so high that they would dominate the mass of the cosmos, and we should be able to detect them with relative ease. Yet, despite decades of dedicated searching with highly sensitive experiments, not a single definitive magnetic monopole has ever been observed. So, where did they all go? This glaring contradiction between theory and observation was a major crisis for cosmology in the late 20th century. The overwhelming absence of these predicted particles threatened to undermine not just grand unified theories, but our entire picture of the hot Big Bang. If the universe was as hot and dense as we believe, then the conditions for creating monopoles were unavoidable. Their non-appearance suggests something is profoundly wrong with our model. This is where cosmic inflation provides a spectacular and simple solution. Remember that inflationary expansion didn't just make the universe large, it made it unimaginably, incomprehensibly vast. The key idea is that inflation would have occurred after the phase transition that produced monopoles. Imagine a room filled with a fine, evenly distributed dust. This dust represents the magnetic monopoles created in great abundance in a tiny, primordial volume of space. Now, imagine that room suddenly expands to the size of our entire observable universe. The dust particles are still there, but they are now so incredibly far apart from one another that the chance of finding a single speck in the space we can observe becomes virtually zero. This is precisely what inflation did. It took that initial, dense soup of monopoles and stretched the space between them by a factor of trillions upon trillions. The density of any pre-existing particles, including these exotic relics, was diluted to such an extreme degree that the average number of monopoles in our entire observable universe could easily be less than one. They weren't destroyed, they were simply pushed beyond our cosmological horizon, their density reduced to undetectable levels. Inflation effectively cleansed our local patch of the universe of these troublesome relics, rendering them invisible to our experiments and allowing the universe we observe to exist without being overrun by their immense mass. The resolution of the monopole problem is often cited as one of the three great observational triumphs of inflation, alongside solving the horizon and flatness problems. It demonstrates the theory's power not just to explain what we do see, but also to account for what we don't see. It shows how an event in the first instance of time could have set the stage for a universe that appears clean and well-behaved, free from the chaotic clutter that our best particle physics suggests should be there. This success, however, comes with a fascinating caveat. While inflation dilutes any monopoles created before it began, some models suggest that a second, much later phase transition could potentially produce a new population of monopoles after inflation had ended. These would not have been diluted, and their predicted density, while much lower than the pre-inflationary abundance, could still be within the reach of future experiments. So the hunt is not entirely over. Scientists continue to search for these elusive particles in cosmic rays, in particle accelerators like the Large Hadron Collider, and even in ancient mica crystals deep underground, which could potentially trap a monopole as it passes through. Finding one would be a monumental discovery, confirming a key prediction of grand unified theories, and giving us a direct probe into the universe at energy scales 1,000,000,000,000 times higher than what we can create in our labs. The mystery of the magnetic monopole, therefore, remains a powerful driver of both theoretical and experimental physics, a ghost from the early universe whose absence confirmed one of our boldest ideas, and whose potential discovery could unlock the next great revolution in our understanding of fundamental forces. This concept pushes us to confront one of the most astounding implications of the entire inflationary framework, moving from a single, unique universe to a reality of literally cosmic proportions. The idea is known as the multiverse, and it emerges naturally from a specific class of inflationary models called eternal inflation. The logic goes like this: if the inflated field, that driver of exponential expansion, had certain quantum properties, then the process of inflation might not have been a one-time, everywhere-at-once event that started and stopped uniformly. Instead, think of it like a pot of water coming to a boil. In most areas, the inflated field would have rolled down its energy hill, ending inflation and creating a stable, reheated region, a bubble of normal space-time like our own universe. But in other regions, thanks to random quantum jumps, the field could have been kicked back up the energy hill, remaining in that high-energy, inflating state. In these patches, inflation would continue, and as it did, it would expand far faster than the stable bubbles forming within it. The result is a self-replicating, ever-growing fractal of space-time. The overall meta-universe is in a perpetual state of inflation, while within it, countless isolated pocket universes, or bubble universes, continuously nucleate, each one a separate cosmic domain with its own local laws of physics. Our entire observable universe, with its hundreds of billions of galaxies, would then be just one single bubble in this infinite cosmic foam. What makes this idea so revolutionary and so unsettling is what happens inside each of these bubbles. The specific way the inflated field settles down at the end of inflation, a process physicists call the graceful exit, determines the local properties of that pocket universe. This includes the fundamental constants of nature, the strength of gravity, the mass of an electron, the charge of a proton, the relative strength of the nuclear forces. In our universe, these values seem exquisitely fine-tuned for the emergence of complex structure and life. If the force of gravity were slightly stronger, stars would burn out too quickly. If the weak nuclear force were slightly weaker, the heavy elements necessary for planets and life might never have been forged in stellar furnaces. The multiverse hypothesis offers a dramatic explanation for this apparent fine-tuning. If there are an infinite or near-infinite number of these pocket universes, then every possible combination of physical constants and laws will be realized somewhere. In the vast majority of these universes, the constants will be wrong. They might be empty or collapse instantly back into a singularity or be composed of featureless radiation. But in a tiny, tiny fraction of bubbles, the numbers will, by pure chance, line up perfectly to allow for galaxies, stars, planets, and life. We, of course, find ourselves in one of those rare, hospitable bubbles. This is the anthropic principle in its most robust form. The universe isn't fine-tuned for us. We exist because we live in one of the few universes that could support us. It shifts the question from why are the laws of physics so perfect to what is the statistical distribution of laws across the wider multiverse. This line of reasoning has profound philosophical consequences that ripple through cosmology and even touch our understanding of our own place in the cosmos. It challenges the very foundation of the scientific method, which is based on the principle of repeatability and testable prediction. If our universe is just one random sample from an endless ensemble, then the specific laws we measure may not be fundamental truths, but merely local environmental accidents. The dream of a single, elegant theory of everything that explains why the constants must have the values they do could be an illusion. Instead, there might be a vast landscape of possible physical laws, and we simply inhabit one small valley in that landscape. This introduces a kind of cosmic humility, demoting our universe from a special, central creation to what might be a mundane, average specimen in an unfathomably vast collection. For some, this is a deeply unsatisfying conclusion, seemingly replacing definitive explanation with a cosmic lottery. For others, it's a liberating expansion of reality's possibilities, suggesting that every conceivable world truly exists somewhere in the multiverse plenum. The critical challenge, of course, is evidence. How could we possibly test for the existence of other universes that are, by definition, beyond our cosmic horizon and disconnected from our space-time? Some theorists suggest that if our bubble universe collided with a neighboring one in the distant past, the immense energy of that impact could have left a peculiar, asymmetric imprint on the cosmic microwave background, a kind of cosmic bruise. Astronomers have searched for such signatures, but so far none have been conclusively found. Others propose that the specific pattern of gravitational waves from inflation, if we can ever detect them, might carry a fingerprint indicative of the multiverse background from which our bubble emerged. The debate surrounding the multiverse is as much about the nature of science itself as it is about cosmology. Is a theory that predicts an infinite number of unobservable universes still scientific? Proponents argue that if a theory like eternal inflation is the most natural and consistent consequence of our best models, and if it explains otherwise baffling observations like fine-tuning, then we should take its predictions seriously, even if direct confirmation remains elusive. The multiverse hypothesis remains one of the most speculative yet compelling frontiers of modern thought, a direct and staggering consequence of taking our theory of cosmic origins to its ultimate logical extreme. But all of this discussion about the trigger for inflation and the multiverse inevitably leads us to an even more profound, and perhaps the ultimate mystery: what, if anything, came before? We've been talking about cosmic inflation as this explosive starting pistol for the universe as we know it, but was it truly the absolute beginning, the first moment of time itself? Or was it merely a transitional phase, a cosmic reset button pressed within a much larger, and possibly eternal, cycle of existence? This question pushes our theories into realms where our current understanding of physics completely breaks down, confronting the enigmatic nature of the initial singularity and the physics of the pre-inflationary universe. The classical Big Bang model points toward a singularity, a point of infinite density and temperature where the known laws of physics cease to have any meaning. In this view, time itself began at that moment. Cosmic inflation was then proposed, in part, to avoid this mathematical and conceptual nightmare, providing a more physically plausible description of the universe's earliest moments. But does inflation itself truly eliminate the need for a beginning, or does it simply push the singularity problem one step further back? If we trace the inflationary expansion backward in time, we still seem to arrive at a point where the universe was incredibly hot, dense, and small, a state that may still be singular in nature. The challenge is that our current theories of gravity, described by Einstein's general relativity, and our theories of the quantum world are fundamentally incompatible at these extreme energies. To understand what happened at or before the start of inflation, we need a theory of quantum gravity, a framework that can describe how space and time themselves behave under such inconceivable conditions. This takes us to the Planck epoch, the first 10 to the minus 43 seconds of the universe, a timescale so short it defies imagination, where the universe was a seething, chaotic foam of quantum spacetime. So, what are the possibilities for this pre-inflationary realm? One compelling idea is that of a big bounce. Instead of a universe born from nothing in a single, definitive beginning, this theory proposes an eternal cycle of expansion and contraction. Imagine a previous universe much like our own that eventually exhausted its potential for expansion and began to collapse under its own gravity. This contraction wouldn't necessarily lead to a final, destructive singularity. Instead, thanks to quantum effects at the highest energies, the collapse could reach a maximum density and then bounce back outward, triggering a new period of rapid expansion, our cosmic inflation. In this cyclical model, the Big Bang wasn't a creation event but a rebirth. Our universe is simply the latest iteration in an endless cosmic cycle, with each bounce resetting the conditions and allowing for a new beginning. This elegantly sidesteps the philosophically troubling concept of a true beginning from nothing, suggesting instead that time is infinite with no start and no end. The challenge, of course, is that any evidence from the previous cycle would have been utterly scrambled and erased by the violent processes of the bounce and the subsequent inflationary expansion, making it incredibly difficult to find any observational proof that we are part of a much older cosmic sequence. Another radical possibility is that our universe is not unique at all, but a child of a larger meta-reality. Some models of string theory and eternal inflation suggest that our inflationary bubble was born from a quantum fluctuation in a pre-existing, eternally inflating spacetime. In this view, the before wasn't a contracting universe, but a different, larger dimensional reality from which our four-dimensional space-time spontaneously nucleated, much like a bubble of steam forming in a pot of boiling water. This parent universe could have entirely different physical laws and dimensions, making the question of what came before even more complex and potentially unanswerable from our limited vantage point. A related and perhaps the most mind-bending idea of all is that the universe and time itself could have emerged from a state of pure geometry, a timeless, unchanging mathematical structure. In this scenario, there is no before in a temporal sense, because time is a property that only came into existence as the universe cooled and expanded from its initial state. Asking what happened before the Big Bang would be as meaningless as asking what is north of the North Pole. The fundamental obstacle to answering these questions is the sheer energy scale involved. Probing the Planck era requires energies a trillion times greater than what our most powerful particle colliders can produce. The universe, in its first instant, was its own ultimate laboratory, conducting experiments at energies we can only dream of recreating. So how can we possibly hope to test these ideas? One potential window is through the faintest of cosmic imprints. If the pre-inflationary universe was not perfectly smooth and symmetric, but had some residual structure or asymmetry from a previous phase, it's conceivable that traces of that structure could have survived the inflationary expansion. These would appear as subtle, large-scale anomalies in the cosmic microwave background, unexpected patterns or alignments in the temperature fluctuations that deviate from the predictions of standard inflation. Astronomers have, in fact, identified a few curious, large-scale anomalies in the CMB data, such as a mysterious axis of evil, where fluctuations seem slightly aligned across the sky. While these could simply be statistical flukes or artifacts of how we process the data, they are precisely the kind of unexpected signature that could point to a fossil from a time before inflation. Another, even more speculative possibility is that the primordial gravitational waves we are so desperately searching for could carry a specific signature imprinted by the physics of the bounce or the quantum gravity state that preceded them. Their specific frequency and amplitude spectrum could, in theory, tell us not just about inflation, but about the conditions that gave birth to it. Ultimately, the mystery of the initial singularity and pre-inflation physics represents the final frontier of cosmology. It's where our hard-won scientific knowledge meets the deepest philosophical questions about existence, time, and the nature of reality. Whether our universe had a definitive beginning or has always existed in some form is a question that has captivated humanity for millennia. Modern science has brought us to the very threshold of an answer, providing us with powerful tools like inflation and quantum mechanics to frame the question with unprecedented precision. Yet, the answer remains just beyond our grasp, hidden behind the veil of the Planck scale. The search for it is driving the development of new, more complete theories like loop quantum gravity and string theory, and inspiring next-generation telescopes and experiments. It forces us to reconsider the very meaning of beginning, and reminds us that our cosmic story, as vast and detailed as it has become, may still have its most important chapter waiting to be written. This brings us to a foundational conflict that lies at the very heart of our quest to understand inflation, a puzzle so deep it challenges our description of reality itself. We've been talking about the universe's rapid expansion as if it were a smooth, continuous stretching of a rubber sheet, governed perfectly by Einstein's general relativity. And for large-scale descriptions, that works brilliantly. But to truly grasp what was happening in that first sliver of a second, when the entire cosmos was smaller than a single atom, we have to venture into the quantum realm. And here we hit a wall: the quantum gravity conundrum. The problem is that our two most successful theories of physics, general relativity and quantum mechanics, are fundamentally incompatible. General relativity paints a beautiful picture of a smooth, continuous spacetime that warps and curves in response to matter and energy. It's a classical, deterministic picture. Quantum mechanics, on the other hand, reveals a world that is inherently fuzzy, probabilistic, and quantized, where particles can be in multiple places at once and empty space seethes with unpredictable energy. Both theories are spectacularly accurate in their own domains, but when pushed to the extreme energies and minuscule scales of the Planck epoch, the very environment in which inflation began, they produce complete nonsense. The equations of general relativity break down, predicting infinities where there should be physical answers. To truly understand the physics of the inflationary epoch, we need a theory that can marry these two conflicting views into a single, coherent framework, a theory of quantum gravity. Without it, our description of the universe's birth is like trying to write a novel with only half the alphabet. What does this conflict actually look like when we apply it to the very fabric of space and time? Imagine zooming in on space-time with a hypothetical microscope of infinite power. According to general relativity, the view would remain smooth and continuous all the way down. But quantum mechanics suggests something far stranger. At the tiniest conceivable scale, the Planck length, which is about 10 to the negative 35 meters, space-time itself should cease to be a smooth continuum. Instead, it's theorized to become a bubbling, foaming, dynamic frenzy often called quantum foam. In this realm, the very concepts of here and now lose their meaning. Tiny wormholes might flicker in and out of existence. Virtual black holes could pop into being and evaporate almost instantly. It's a turbulent, probabilistic sea of geometry. This is the environment in which the inflationary mechanism was triggered. The inflated field wasn't just sitting in a smooth, classical landscape. It was a quantum entity fluctuating wildly within this frothing spacetime foam. Our current model of inflation largely glosses over this. It treats the beginning of inflation as happening within a pre-existing, smooth, classical spacetime background. But this is almost certainly an approximation, a useful fiction that gets us most of the way there but fails at the ultimate moment of origin. The true ignition of inflation was likely a quantum event, a fluctuation in the geometry of spacetime itself that allowed a tiny patch to tunnel into the inflating state. Without a theory of quantum gravity, we cannot describe this transition. We don't know if the universe tunneled from nothing, emerged from a bounce, or was born from the collapse of a previous state. We are missing the first and most important page of the story. This isn't just a philosophical problem. It has direct, observable consequences for the predictions inflation makes. The entire structure of the modern universe originated from those tiny quantum fluctuations in the inflated field that were stretched to cosmic proportions. But those fluctuations didn't occur in a serene, classical void. They were born in the chaotic maelstrom of quantum spacetime. A proper theory of quantum gravity would tell us how that initial foaminess affected the seeds of structure. Did it alter their statistical properties? Could it have imprinted a specific signature on the gravitational waves from that era? The current models assume a smooth background and produce fluctuations that are nearly perfectly scale invariant and Gaussian, which matches our observations of the cosmic microwave background spectacularly well. But what if subtle deviations from this perfect pattern, tiny anomalies that we might one day detect with more sensitive instruments, are actually the fossilized imprint of spacetime's quantum graininess? Finding such a signature would be like discovering the first fossil of a previously unknown ancestor, providing our first direct glimpse into the quantum gravity regime. The hunt for these primordial gravitational waves is in many ways a hunt for the effects of quantum gravity. Detecting them would not only confirm inflation, but could also provide a crucial data point for discriminating between different proposed theories of quantum gravity, by revealing the specific spectrum of those waves imprinted by the physics of the Planck scale. So, what are the contenders in the race to become this ultimate theory? The two most prominent candidates are string theory and loop quantum gravity. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings and membranes. The different vibrations of these strings give rise to all the particles and forces we see, and the theory necessarily includes a quantum description of gravity. One of its most provocative insights is that it may require extra dimensions of space beyond the three we experience. Loop quantum gravity takes a different, more geometric approach. It proposes that space itself is not continuous, but is woven from a network of finite, quantized loops, a literal fabric of spacetime. In this picture, area and volume come in discrete, tiny packets, much like energy in an atom exists in specific levels. This provides a natural cutoff that prevents the infinities that plague general relativity. Both theories offer potential pathways to understand the pre-inflationary universe. For instance, some models in loop quantum gravity suggest the Big Bang could be replaced by a big bounce, avoiding the singularity entirely. String theory, with its vast landscape of possible vacuum states, provides a natural setting for the eternal inflation and multiverse scenarios we discussed earlier. Yet, despite decades of brilliant work, neither theory has yet produced a definitive, testable prediction that can be verified with our current technology. They remain magnificent mathematical architectures, waiting for an experimental key to unlock their connection to our physical reality. The inflationary epoch stands as the one event in cosmic history where the effects of quantum gravity were not just a minor correction, but the main event. Until we solve this conundrum, our understanding of the universe's origin will remain tantalizingly incomplete, a breathtaking story with its most crucial chapter still unwritten. Even as inflation elegantly resolves so many of the universe's initial puzzles, it introduces a perplexing challenge of its own, one that strikes at the very elegance for which it is so often praised. This is the problem of fine-tuning, and it forces us to ask whether our beautiful solution might simply be disguising a deeper level of cosmic coincidence. To produce a universe that is flat, smooth, and filled with the right kind of structures like galaxies and stars, the parameters of the inflationary model itself must be set with what seems like extraordinary precision. It's as if the universe's initial conditions were dialed in to an impossibly specific combination on a cosmic control panel. Consider the inflattened field itself. For inflation to start, persist long enough, and then end correctly, the shape of this field's potential energy landscape has to be just right. Imagine a very gentle, almost flat hill stretching for a great distance. This gentle slope is crucial. If the hill were too steep, the inflated field would have rolled down too quickly, ending inflation almost before it began and failing to solve the horizon and flatness problems. The universe would have remained small and highly curved. Conversely, if the slope were too shallow, the field might have gotten stuck, leading to eternal inflation in that region and never producing a stable bubble like our own universe. The required flatness of this potential is not just a minor detail. It must be exceptionally, almost unnaturally flat to match our observations. This is not a parameter that the theory predicts. It is a parameter that we must carefully input into the theory to get the desired outcome. This precise tuning extends to the energy scale of inflation. The amount of energy driving the expansion had to fall within a very narrow window. If the inflationary energy were significantly higher, the quantum fluctuations that were stretched into cosmic seeds would have been far too large. The resulting universe would be incredibly lumpy, with gravitational collapse creating vast numbers of black holes rather than well-ordered galaxies, a chaotic and likely uninhabitable cosmos. If the energy were much lower, the fluctuations would have been too feeble. Gravity would have had almost no initial irregularities to work with, resulting in a universe that remained far too smooth and diffuse, preventing the formation of any interesting structures at all. The fact that our universe exhibits a beautiful, intricate cosmic web of galaxies and voids tells us that the inflationary energy was, against all odds, calibrated to a perfect sweet spot. But the theory itself doesn't explain why it was set to that specific value. It appears as another piece of incredibly good fortune, a lucky break written into the laws of physics. For some critics, this reliance on fine-tuning is a significant weakness. They argue that inflation hasn't so much solved the original fine-tuning problems of the horizon and flatness, as it has simply shifted them to a new, more fundamental level. Instead of asking why the initial universe was so smooth and flat, we are now asking why the properties of the inflated field were so exquisitely tailored to produce that smoothness and flatness. It's like trading one mystery for another, arguably more profound one. This has led to a spirited debate within cosmology. Is inflation a truly fundamental explanation, or is it more of a descriptive mechanism that works beautifully but whose underlying cause remains completely unknown? The need for these precise initial conditions can feel unsatisfying to physicists who seek theories based on necessity and robust prediction, not on seemingly arbitrary and delicate adjustments. This isn't just an academic quibble, it gets to the heart of what we consider a good scientific theory. A theory that requires a long list of perfectly chosen numbers to match reality can feel more like a description than an explanation. Yet, proponents of inflation offer several compelling counterarguments. One of the most powerful is the concept of the multiverse, which we touched on earlier. In an eternally inflating meta-universe where countless bubble universes are continuously being born, every conceivable combination of inflated field parameters will be realized somewhere. In the overwhelming majority of these bubbles, the parameters will be wrong: the slope too steep or too shallow, the energy too high or too low. Those universes will be stillborn, empty, or short-lived. But in a tiny, statistically inevitable fraction of bubbles, the numbers will, by pure chance, line up perfectly. We, of course, find ourselves in one of those rare, hospitable bubbles where inflation lasted just the right amount of time and produced fluctuations of just the right magnitude to allow for galaxies, stars, planets, and life. From this perspective, the apparent fine-tuning isn't a problem to be solved. It's a consequence of our own existence. We couldn't possibly be asking these questions in a universe that wasn't tuned for structure. This application of the anthropic principle provides a dramatic, if controversial, way out of the fine-tuning dilemma, suggesting that the parameters of our universe are not laws but local accidents. Another possibility is that we simply haven't found the complete theory yet. Our current model of inflation might be a low-energy approximation of a much deeper, more fundamental theory, such as string theory or a complete theory of quantum gravity. In this more complete framework, the shape of the inflated potential and the energy scale of inflation might not be free parameters at all. They could be derived necessarily from the mathematics of the higher theory, the only possible outcome given the fundamental laws. What appears to us as fine-tuning from our limited vantage point might, in the full theory, be an unavoidable mathematical truth. The hunt for this deeper theory is therefore not just an abstract pursuit. It is directly linked to resolving one of the most persistent philosophical challenges of modern cosmology. The fine-tuning problem, rather than being a fatal flaw for inflation, acts as a powerful guidepost, pointing us toward the next great theoretical frontier and reminding us that our current understanding, for all its brilliance, is almost certainly incomplete. While the theory of cosmic inflation has become the leading narrative for our universe's earliest moments, it's crucial to remember that science thrives on competition and alternative ideas. The quest to understand the beginning of everything is far from settled, and a number of compelling rival theories challenge the inflationary paradigm, each offering a radically different vision of that first instant. These aren't just minor tweaks, they propose entirely new cosmologies that attempt to solve the same fundamental problems: the horizon and flatness puzzles, without relying on a period of fantastically rapid expansion. One of the most prominent alternatives is the cyclic model, a concept that replaces the single, definitive Big Bang with an endless, timeless cycle of cosmic death and rebirth. In this breathtaking vision, our universe is not the first and only one, but merely the latest incarnation in an infinite sequence. The model suggests that what we perceive as the Big Bang was actually a big bounce. Imagine a previous universe much like our own that eventually expanded to a maximum size. Instead of expanding forever, the collective gravitational pull of all its matter, including dark energy, eventually caused it to stop and begin contracting. This contraction wouldn't lead to a catastrophic singularity, however. Thanks to effects from string theory or loop quantum gravity, the universe would reach a maximum density and then bounce back outward, triggering a new period of expansion that we now call our Big Bang. This process would then repeat cycle after cycle for all eternity. So, how does this solve the horizon problem? In this model, the universe before ours had an incredibly long time, trillions upon trillions of years, to homogenize and reach a uniform temperature through the same old-fashioned processes of thermal equilibrium. The bounce and subsequent expansion then preserve that smoothness, handing a pre-solved horizon problem to the new universe. The flatness is similarly addressed. Each cycle of expansion and contraction naturally drives the geometry of the universe toward flatness, much like how stretching and relaxing a rubber sheet over and over again smooths out its wrinkles. A key prediction of some cyclic models is that they do not produce a primordial gravitational wave background with the same strength as inflation, meaning that if future experiments continue to find no evidence of these waves, it could be a major point in favor of a cyclical cosmos. Another fascinating challenger emerging from string theory is the ekpyrotic universe model. The name itself, derived from the Greek word for conflagration or fire, hints at its dramatic nature. This scenario paints a picture of our three-dimensional universe as a three-dimensional brane existing within a higher dimensional bulk reality. In this setup, the Big Bang was not an explosion from a singularity, but a colossal, transformative collision between our brane and a neighboring parallel brane. Before the collision, the two branes were largely empty, cold, and flat. As they moved toward each other in the higher dimensional space, the energy of their impending impact created quantum fluctuations. When they finally collided, the immense kinetic energy of the crash was converted into the hot, dense soup of particles that became our hot Big Bang universe. This model elegantly sidesteps the need for inflation. The horizon problem is solved because the pre-collision branes were in a state that allowed for causal contact across their entire expanse. they had ample time to smooth themselves out long before the collision that created our cosmic epoch. The flatness problem is resolved because the branes themselves are naturally flat, and the collision doesn't introduce enough energy to warp them on the largest scales. The ekpyrotic model makes a very distinctive prediction about the primordial seeds for structure. While inflation stretches quantum fluctuations, the ekpyrotic scenario generates its fluctuations through the classical motion of the colliding branes. This process is theorized to produce a spectrum of fluctuations that is not perfectly scale invariant, potentially with a specific type of signature that could be distinguished from inflationary predictions in future, ultra-precise measurements of the cosmic microwave background. A third and conceptually very different approach is string gas cosmology. This framework tries to build a picture of the very early universe using the fundamental principles of string theory from the very start, rather than adding them on later. In this model, the universe begins as a hot, dense gas of the fundamental strings proposed by string theory, all confined to a small, compact space. In these initial conditions, the strings are constantly interacting and winding around the compact dimensions of the universe, preventing it from expanding. The key moment comes when the temperature of this string gas reaches a specific point, triggering a phase transition. This transition allows the winding modes of the strings to annihilate, suddenly releasing the pressure that was holding the universe back and allowing 3 of the spatial dimensions to rapidly expand. This becomes our observed Big Bang expansion, but without a prior period of inflationary acceleration. String gas cosmology addresses the horizon problem through the thermal nature of the initial string gas. Because the strings were in a hot, thermal state, they were in constant contact and could easily achieve uniformity across the entire tiny volume. The subsequent expansion then preserves that uniformity, just as in the other models. Its most unique prediction lies in the structure of the universe. This model suggests that the distribution of the very first structures should have been truly scale invariant, meaning the initial seeds for galaxies and clusters of galaxies should have been statistically identical on all scales, unlike the nearly scale invariant spectrum predicted by inflation. Furthermore, it predicts a specific and potentially detectable signature in the polarization of the cosmic microwave background that differs from the B-mode pattern sought as evidence for inflation. The existence of these competing theories is a sign of a healthy, dynamic field of science. They force cosmologists to sharpen their arguments and look for the specific, observable fingerprints that can distinguish one grand story from another. The ongoing debate isn't just about which model is more mathematically elegant. It's about which one makes predictions that match the hard data we collect from the cosmos. The search for primordial gravitational waves remains a critical battleground. A clear detection would be a massive victory for standard inflation. Their continued absence or the discovery of a different kind of pattern in the CMB could open the door wide for a cyclic, ekpyrotic, or string gas universe. This competition ensures that our understanding of cosmic origins remains an open and thrilling inquiry, a reminder that the greatest mysteries of the universe are still very much up for grabs. But as we explore these cosmic conundrums, a truly mind-bending possibility emerges, one that connects the universe's first moment to its ultimate fate. We've talked about the inflated field, that mysterious engine of exponential growth in the first fraction of a second. But then, billions of years later, astronomers made a shocking discovery. The universe's expansion isn't just continuing, it's speeding up again, driven by an even more enigmatic force we call dark energy. The haunting question is this: are these two accelerations, one at the dawn of time and one in the present cosmic epoch, somehow related? Could the inflated field and dark energy be two faces of the same fundamental coin? On the surface, the parallels are striking. Both phenomena involve a form of energy inherent to the fabric of space itself that causes a repulsive gravitational effect, pushing the universe apart instead of pulling it together. Both operate on scales that dwarf human comprehension. one shaping the entire cosmos in an instant and the other governing its long-term evolution across billions of years. The inflated field's energy was unimaginably dense and short-lived, a colossal burst that faded as the field decayed. Dark energy, by contrast, appears incredibly feeble and persistent, a whisper-thin force whose influence only became dominant after galaxies had formed and evolved. Yet, the underlying mechanism could, in theory, be similar, a scalar field, much like the hypothesized inflaton, that permeates all of space and whose energy density dictates the expansion rate. Exploring this connection forces us into a fascinating detective story with two very different sets of clues. If dark energy is simply the cosmological constant, a fixed energy density of the vacuum as Einstein once proposed, then it might be entirely separate from inflation. This would mean our universe is governed by two distinct and unrelated forms of repulsive gravity, one for the beginning and one for the end. However, many theorists find this duality unsatisfying, a cosmic coincidence that begs for a deeper, unified explanation. What if the inflated field never completely vanished? What if, after its dramatic decay and reheating of the universe, a tiny remnant of that field lingered, frozen at a very low energy level? Over the eons, as the universe expanded and matter diluted, this faint leftover could have gradually become the dominant component, reasserting itself as the dark energy we observe today. In this compelling narrative, the universe's first breath and its final sigh are driven by the same underlying entity, a single field that has orchestrated the cosmos's dynamics from start to finish. Another, more dynamic possibility is that dark energy isn't a constant at all, but a slowly evolving field sometimes called quintessence, a cosmic cousin to the inflaton. Unlike the cosmological constant, quintessence can change over time, its energy density gradually shifting. This introduces a thrilling variable into the cosmic future. If dark energy is a form of quintessence, it might eventually decay away, allowing the universe to evolve in ways we can't yet predict. Or it could even reverse sign, leading to a catastrophic big rip where the fabric of spacetime itself is torn apart. The implications of a link are profound, touching on everything from the ultimate fate of the cosmos to the very nature of physical law. If inflation and dark energy are connected, it suggests a kind of cosmic symmetry, a cyclical rhythm of acceleration woven into the laws of physics. It would mean that the force that made the universe large and flat is also the force that will determine its final destiny, tying the beginning and the end together in a single, elegant theoretical framework. However, the evidence remains elusive and the challenges are immense. The energy scale of the inflated field was astronomically higher than the measured energy density of dark energy, by a factor of around 120 orders of magnitude. This is arguably the worst theoretical prediction in the entire history of physics, highlighting a gap in our understanding so vast that it points toward a fundamental missing piece. Bridging this gap is one of the most active pursuits in theoretical cosmology, pushing physicists to explore ideas like the string theory landscape, where the value of dark energy is not a fundamental constant but an environmental variable that settled into its current, small value in our particular pocket of the multiverse. The mystery of whether dark energy is the ghost of inflation past or an entirely new actor on the cosmic stage remains one of the most captivating and unresolved questions, a puzzle that challenges us to see the entire history of the universe not as a series of disconnected events, but as a single, continuous, and deeply interconnected story. But this incredible stretching of the universe during its first moments presents us with a paradox so deep it challenges our understanding of information itself. Think about the world around you: every mountain, every ocean, every person, every piece of data on the internet. All of this represents an immense amount of information, a specific and complex arrangement of matter and energy that defines our reality. Now, rewind the cosmic clock back to the instant before inflation began. Our entire observable universe, everything we can possibly see, was compressed into a region of space smaller than a single proton. This microscopic quantum patch was subject to the bizarre rules of quantum mechanics, where properties are fuzzy and probabilities reign. So here is the haunting question. How can the nearly infinite complexity of our present-day cosmos, with its hundreds of billions of galaxies, possibly be encoded within the limited information capacity of that initial subatomic speck? This is the cosmological information paradox, and it forces us to confront whether the universe operates like a perfect, lossless data compression algorithm, or if something fundamental is missing from our picture. To grasp the scale of this puzzle, consider a simple analogy. Imagine you have a beautiful, high-definition movie. The raw data for that film is enormous, requiring gigabytes of storage. Now, imagine you want to compress that movie file down to a size smaller than a single pixel on your screen. With our current technology, this is impossible. You would irrevocably lose almost all the information, and the original movie could never be recovered. Inflation seems to have done the opposite. It took a seed of unimaginably small size and expanded it into a cosmos of unbelievable complexity and structure. But where did all that new information come from? The galaxies and stars we see today aren't just stretched versions of the same few bits of data. They are novel structures that formed over billions of years through gravitational collapse and complex physical processes. It appears as though the universe has created information out of nothing, which would violate fundamental principles of quantum mechanics that state information cannot be created or destroyed, only transformed. The paradox is this: if information is conserved, the entire cosmic story must have been somehow pre-written in that initial quantum fluctuation. But that seems to imply a level of predetermined destiny that makes physicists deeply uncomfortable, as it clashes with our understanding of quantum randomness and free will. The resolution may lie in a more nuanced understanding of what we mean by information in a cosmological context. In physics, information isn't about meaning or content like in a book. It refers to the specific quantum states of all the fundamental particles and fields. The key might be that the initial quantum patch, while tiny in size, was not simple. According to quantum mechanics, the number of possible states for a system is related to its surface area, not its volume, a concept famously explored in the holographic principle. This principle suggests that all the information describing a volume of space can be thought of as encoded on a lower dimensional boundary surrounding it, like a three-dimensional movie being projected from a two-dimensional surface. In the context of inflation, it's possible that the entire informational content of our universe was indeed present on the boundary of that initial speck, and the process of inflation simply unfolded or displayed that information across the vast three-dimensional canvas we now inhabit. In this view, the universe didn't create new information. It just translated a holographic blueprint into a sprawling, three-dimensional reality. The complexity we see today was always there, not in the classical sense of a detailed map, but in the quantum potential of the initial state. Yet, this leads to another layer of the mystery involving quantum entanglement. The universe we observe is filled with systems that are causally connected, their histories intertwined. This interconnectedness itself carries information. During inflation, the rapid stretching of space would have massively entangled the quantum states of different regions. What we perceive as separate galaxies today were once part of a single, entangled quantum system. The information about our universe, therefore, may not be stored in any one place, but in the global pattern of entanglement between all its parts. This is a profoundly non-local picture of reality, where the true description of the cosmos is not found by cataloging individual stars, but by understanding the invisible quantum threads that stitch the entire cosmic tapestry together. The apparent creation of information is then an illusion, a consequence of our limited local perspective. From a God's eye view of the entire system, the total information was conserved all along, merely transforming from a state of dense quantum entanglement into the classical, separated structures we now observe. Unraveling this puzzle is not just an academic exercise. It pushes us toward a theory of quantum gravity that can properly describe how information is processed and preserved during the most extreme events, from the birth of the universe to the evaporation of black holes, weaving together the largest and smallest scales of existence into a single, coherent picture of reality. This brings us to a deeply technical but utterly foundational puzzle that emerges directly from the concept of an eternally inflating multiverse, a conundrum so severe it threatens to undermine our very ability to do science in such a cosmos. It's called the measure problem, and it asks a deceptively simple question. In a reality where everything that can happen does happen, and happens an infinite number of times, how can we possibly say that anything is more or less likely than anything else? The core of the issue is infinity itself. Eternal inflation suggests that the meta-universe is not just vast, but truly infinite in both space and time, continuously giving birth to an endless number of pocket universes. Within this infinite ensemble, every single possible combination of physical constants, every possible arrangement of matter, and every conceivable historical timeline will be realized. There will be an infinite number of universes with laws of physics identical to our own, and an infinite number where gravity is repulsive, where protons are unstable, and where the universe is a featureless sea of radiation. When you have two infinite sets, comparing them becomes a mathematical nightmare. How do you calculate the probability of finding yourself in a universe like ours? If you try to take the ratio, you get infinity divided by infinity, which is not a number. It's an undefined, meaningless expression. This makes it seemingly impossible to make any probabilistic prediction at all. Why do we observe a universe with 3 spatial dimensions and a cosmological constant of a certain value? In an infinite multiverse, we couldn't claim it's because that value is more probable. All outcomes are equally represented in the dreadful democracy of infinity. The problem becomes starkly clear when we consider the anthropic principle, which we rely on to explain why we live in such a finely tuned universe. The logic is that we can only exist in a universe that allows for observers, so we shouldn't be surprised to find ourselves in one. But for this reasoning to hold any weight, life-permitting universes must be more common than lifeless ones in the overall multiverse population. Yet, if the multiverse is infinite, there are an infinite number of habitable universes and an infinite number of barren ones. Without a way to define a measure, a specific mathematical procedure for counting the universes in a finite, comparable way, the statement that habitable universes are common or rare loses all meaning. It's like trying to determine whether there are more odd numbers than even numbers. Both sets are infinite, so the question is ill-posed without a specific counting scheme. This throws a wrench into the entire predictive machinery of cosmology. We use probability every day to test our theories against observations. If the multiverse scenario makes all probabilities effectively 0 or 1, then it can't be falsified or confirmed. It risks becoming what some critics fear, an untestable metaphysical idea rather than a scientific one. So how do physicists attempt to solve this? They look for a sensible way to regulate the infinity, to impose a cutoff that allows for finite comparisons. Imagine you are a demographer trying to determine the population density of a country. You don't just say the population and area are both infinite. You take a finite sample, like 1 square kilometer, and count the people within it. Cosmologists trying to solve the measure problem are searching for the cosmic equivalent of that fair and unbiased square kilometer. One popular approach is the volume measure. This method proposes that we should count pocket universes based on their physical volume in the multiverse at a specific moment in time. The idea is that some types of universes, particularly those where inflation continues for longer, end up occupying a larger share of the total multiverse space. In this picture, a universe like ours might be considered probable if it represents a large fraction of the total volume of the multiverse. However, this approach has a notorious flaw. It's often dominated by the young, rapidly inflating regions. Because inflation is exponential, the parts of the multiverse that are still inflating expand so quickly that they always contain almost all of the volume, making the fraction occupied by stable, reheated bubbles like our own essentially zero. This leads to the baffling prediction that an observer should almost certainly find themselves in the middle of an inflating void, not in a mature universe with galaxies, a clear contradiction with what we actually observe. Another strategy is the causal diamond or world line measure. This method abandons the idea of a God's eye view of the entire multiverse and instead focuses on the perspective of a single observer. It considers only the finite region of spacetime that a single observer can ever causally interact with over their entire history, from the moment the CMB first became transparent to them in the past to the farthest point their future light cone will ever reach. By counting the number of times a particular type of event, like the formation of a planet, occurs within this finite, observer-centered diamond, we can finally get a finite, meaningful probability. This method avoids the problem of infinite volumes by privileging the local, observable reality of the observer, which is, after all, the only reality we can ever actually measure. It often predicts that we should be typical observers within our reference class, which aligns well with the Copernican principle that we do not occupy a privileged position in the cosmos. Yet, even this approach has its own peculiar consequences, sometimes suggesting that we are more likely to be Boltzmann brains, brief, random fluctuations of consciousness in an otherwise empty void, than evolved beings in an ordered universe, another deeply unsettling prediction. The sheer persistence of the measure problem and the fact that so many brilliant minds have proposed such wildly different solutions with equally strange outcomes tells us something profound. It highlights that our intuition, built in a finite, local world, completely fails when confronted with the true implications of infinity. The problem forces us to ask what it really means for a theory to be predictive and whether our current tools of mathematics and probability are even adequate to describe a reality of such limitless scope. The struggle to find a unique, compelling measure is, in essence, a struggle to rebuild the foundation of scientific prediction for the grandest possible stage. Until it is solved, the multiverse remains a breathtakingly beautiful and plausible vision, but one whose scientific core is held in a delicate, uncertain balance, a reminder that our journey to comprehend the totality of existence is still in its very early stages. And so we arrive at a challenge that forces our observational capabilities to their absolute limit, a hunt for the most subtle of ghosts in the cosmic machine. We've seen how the cosmic microwave background is an astonishingly smooth tapestry, a testament to the powerful smoothing effect of inflation. But if you look closely enough with instruments of breathtaking sensitivity, you find that this uniformity is not perfect. It's adorned with tiny, hot and cold spots, the anisotropies that are the seeds of all galactic structure. For decades, the primary goal was to map these spots and confirm they matched the broad predictions of inflation, that they should be nearly scale invariant and have a Gaussian or random statistical distribution. And spectacularly, they do. But now, cosmologists are engaged in a far more delicate pursuit. They are no longer just confirming the theory. They are trying to read the fine print, searching for tiny, systematic deviations from this perfect randomness. These deviations, known as non-Gaussianities, are the next frontier. They are the cosmic equivalent of finding a faint, hidden watermark on a piece of pristine paper, a signature that could tell us exactly which version of the inflationary story is the correct one, or even point toward physics that operates at energies so high they are forever beyond the reach of any particle accelerator. To understand why this hunt is so crucial, picture the early universe not as a perfectly smooth classical field, but as a turbulent quantum sea. The standard story of inflation tells us that the quantum fluctuations in the inflated field were stretched to cosmic sizes, and that these fluctuations were Gaussian. This is a specific statistical term that essentially means they were completely random and uncorrelated. Imagine the static on an old television screen. Each pixel flickers white or black with no connection to its neighbors. That's a Gaussian pattern. In this picture, every hot and cold spot in the CMB is an independent event, a solitary quantum jitter that got magnified. This is a powerful and successful prediction, but it's also what you might call the simplest possible outcome. Many different models of inflation can produce a nearly Gaussian result. So, to move beyond this and distinguish between the myriad of theoretical possibilities, we must look for the tiny failures of this perfect randomness. Non-Gaussianity represents a statistical connection between these fluctuations. It suggests that the hot and cold spots are not entirely independent, that there is a subtle conversation happening between them, a faint correlation that betrays a more complex underlying physics. Finding this signal would be like discovering that the television static, when analyzed with a powerful enough computer, contains hidden, repeating patterns. These patterns are the fossils of interactions that occurred during inflation itself, a snapshot of the inflated field not just fluctuating in isolation, but interacting with itself or with other, as yet unknown fields. The search for this signal is a monumental exercise in statistical cosmology. It involves taking the exquisitely detailed full sky maps produced by satellites like Planck and running them through a battery of sophisticated statistical tests, looking for any sign of a non-random hand at work. Scientists look for specific shapes in the patterns of the temperature variations. For instance, some models predict a particular type of non-Gaussianity where three hotspots form a specific triangular configuration in the data more often than pure chance would allow. The strength and shape of this signal act like a fingerprint. Different models of inflation with different types of inflated potentials and different interactions leave behind distinct non-Gaussian imprints. A detection would therefore be far more than just a confirmation. It would be a diagnostic tool allowing us to rule out vast swaths of the inflationary landscape and hone in on the specific physical reality that drove the universe's birth. It could tell us if the inflated field rolled slowly or quickly down its potential hill, if it interacted strongly with other particles, or if multiple fields were working in concert to drive the expansion. In this way, the hunt for non-Gaussianity is the process of moving from a general, one-size-fits-all theory of inflation to a specific, detailed history of those first moments. But the implications run even deeper. The current data shows that the universe is consistent with a very low level of non-Gaussianity, which aligns with the simplest inflationary models. However, the hunt continues with ever-increasing precision because the stakes are so high. A significant detection would not just refine our model of inflation, it could shatter it, pointing toward phenomena that the standard picture cannot accommodate. For example, certain types of non-Gaussian signatures could be the echo of a cosmic string, a one-dimensional topological defect from the early universe brushing against the primordial plasma. Others might reveal the presence of multiple light fields during inflation, a scenario that generates a much richer and more complex pattern of fluctuations. The most exciting possibility is that a clear non-Gaussian signal could provide a direct window into the realm of quantum gravity. If the fabric of spacetime was truly foamy and discrete at the Planck scale, as some theories suggest, the process of stretching these quantum fluctuations might have imprinted a specific non-Gaussian signature on the CMB, a direct fossil of spacetime's granular nature. The continued, tantalizing absence of a strong signal is itself a powerful piece of information, relentlessly pruning the family tree of viable inflationary models and pushing theorists toward ever more refined and minimal constructions. This meticulous pixel-by-pixel interrogation of the oldest light in the universe is our most promising path to writing the definitive biography of cosmic inflation, transforming it from a compelling paradigm into a detailed, empirical chapter in the history of the cosmos. This trans-Planckian problem is perhaps one of the most conceptually dizzying puzzles of all, because it forces us to admit that the very foundation of our cosmic story might be built on a profound gap in our understanding. Let's break down why this is so troubling. The theory of inflation tells us that the immense galaxies and vast voids we see today grew from infinitesimally small quantum fluctuations that were stretched to cosmic proportions. But to get the universe we observe, we have to trace those fluctuations all the way back. We have to imagine them when they were not just small, but smaller than the smallest possible scale that our current physics can describe, the Planck length. This is a distance of about 10 to the negative 35 meters, a scale so tiny that it's to an atom what an atom is to our entire solar system. At this realm, the very ideas of space and time as smooth, continuous concepts are believed to break down, replaced by a frothing, turbulent quantum foam governed by the unknown laws of quantum gravity. Inflation, in its incredible stretching, essentially took physics from this completely unknown territory and magnified it, writing it across the entire sky. This means the specific pattern of galaxies we see today, the precise arrangement of hot and cold spots in the cosmic microwave background, may be a direct consequence of physical laws that we have not yet discovered. It's as if we're trying to understand a magnificent, high-definition movie, but the master print was created using a technology that is utterly alien to us. Our entire observable universe could be a colossal monument to physics we don't yet comprehend. The heart of the problem lies in what we assume about the initial conditions for these quantum fluctuations. In our standard calculations for inflation, we make a crucial and perhaps naive assumption that the laws of physics as we know them, specifically quantum field theory laid over a smooth, classical spacetime, work perfectly well even for wavelengths far smaller than the Planck length. We essentially extrapolate our known physics straight down into the abyss of the unknown. This is a tremendously useful simplifying assumption, and remarkably, it produces predictions for the CMB that match our observations with stunning accuracy. But from a theoretical standpoint, it's deeply unsatisfying. It's like using Newtonian physics to calculate the trajectory of a rocket and getting the right answer, even though we know that at velocities close to the speed of light, we should be using Einstein's theory of relativity. We got lucky with the rocket, but are we getting lucky with the cosmos? The concern is that our successful predictions might be a kind of cosmic coincidence, and that the true quantum gravity informed beginning would have left a different, more nuanced imprint. By relying on an extrapolation into a regime where our theories are guaranteed to fail, we might be blinding ourselves to the true, deeper story of the universe's birth. So what might actually be happening at these trans-Planckian scales? Without a full theory of quantum gravity, we can only speculate, but the possibilities are fascinating. In some approaches, like loop quantum gravity, space is not continuous. It is woven from a fabric of tiny, discrete, finite loops. This introduces a fundamental granularity to the universe, much like a digital pixel on a screen. If this is true, then there is a literal shortest possible wavelength for any fluctuation. You simply cannot have a wave smaller than the fundamental pixel of space. What would inflation do with such a fluctuation? It wouldn't be stretching a perfectly smooth classical wave. It would be amplifying a fundamentally grainy, discrete piece of information. This could potentially leave a subtle signature in the large-scale structure of the universe, perhaps a slight deviation from perfect scale invariance or a specific type of non-Gaussianity that we could one day detect. Another possibility emerging from string theory is that the concept of a point-like particle breaks down at these scales, replaced by tiny, vibrating strings. This could modify how fluctuations propagate and interact in the early universe, again potentially altering the statistical properties of the seeds that inflation plants. The trans-Planckian problem, therefore, isn't just a philosophical worry. It's a concrete challenge that pushes us to look for specific, faint fingerprints of quantum gravity in our most precise cosmological data. The hunt is to see if the universe's largest structures carry the encoded signature of its smallest possible grains. This brings us to a mystery that touches the very flow of our existence, a puzzle about why time moves in one direction only. Why do we remember yesterday but not tomorrow? Why does a shattered cup never spontaneously reassemble itself? This one-way directionality is what physicists call the arrow of time, and its ultimate origin is one of the most profound questions in all of science. The startling proposal is that the cosmic inflation era didn't just shape the cosmos we see. It may have set the very clockwork of cause and effect into motion, defining for all time what we call the past and the future. To understand this, we have to delve into a concept known as entropy. In simple terms, entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Things move from order to disorder. This is why your tidy room will naturally become messy if you don't clean it, but a messy room will never spontaneously become tidy. This relentless increase in entropy gives us a powerful arrow, pointing from a more ordered past toward a more disordered future. But this presents a monumental puzzle. If the universe is always becoming more disordered, then it must have started in a state of incredibly low entropy, a condition of exquisitely high order. Why was the early universe in such a special, finely tuned state? What set the entropy so incredibly low at the beginning, providing the winding for the cosmic clock to unwind? This is where cosmic inflation offers a breathtakingly elegant solution. Let's revisit what the universe was like at the end of that explosive period of expansion. Remember the process of reheating, where the energy of the inflated field decayed into a hot, dense plasma of particles. This newly created universe was not just hot, it was also in a state of remarkable uniformity and thermal equilibrium. While this might sound chaotic from a thermodynamic perspective, this uniform soup was a state of incredibly low gravitational entropy. It's a subtle but crucial point. A perfectly smooth, evenly distributed gas has nowhere to go gravitationally. It's in a state of maximum stability and order. There are no clumps of matter to create deep gravitational wells, no complex structures, just a featureless high-temperature sea. This is the ultimate low-entropy starting point. Inflation acted as a cosmic reset button, taking whatever came before, whether it was a quantum fluctuation, a bounce, or a multiverse bubble, and processing it into this pristine, orderly, and low-entropy initial condition for the hot Big Bang. It ironed out all the wrinkles, erased any prior complexity, and presented the subsequent universe with a clean, simple, and highly ordered slate from which to begin its long journey toward disorder. From that moment forward, the second law of thermodynamics takes the wheel. The universe had only one way to go, towards higher entropy, but how does a smooth, featureless state become more disordered? The answer is both beautiful and counterintuitive. The universe increases its entropy by becoming more structured and complex, not less. Those tiny quantum fluctuations that inflation stretched across the cosmos were the key. They provided the minuscule imperfections, the seeds of future chaos. Under the relentless pull of gravity, these slightly denser regions began to attract more matter. Gas clouds collapsed to form the first stars. Those stars gathered into galaxies, and galaxies clustered into the vast cosmic web. Every step of this process, every act of gravitational clumping, released enormous amounts of energy and radiation, which flew out into the void, increasing the overall disorder of the universe far more than the local order created by the new structure. A star, for all its brilliant order, is a fantastic engine for increasing entropy. It takes concentrated nuclear fuel and disperses it as light and heat across the cosmos. So, the very formation of every galaxy, every star, every planet, and every person is a direct consequence of the universe's relentless drive toward higher entropy. The arrow of time, the one that gives us our memories and our sense of a fixed past and an open future, is propelled by this cosmic transformation from inflationary smoothness to gravitational complexity. This profound connection reshapes our understanding of our own place in the cosmos. Our ability to think, to remember, to experience life as a sequence of events is not just a biological accident. It is a direct consequence of the universe's initial low-entropy state, a gift from the inflationary epoch. The very reason you can recall what you had for breakfast this morning, but cannot remember what you will have for breakfast tomorrow, is because the past is the direction in which entropy was lower. Our brains and all recording devices are thermodynamically irreversible. They function by increasing entropy within themselves as they form memories. We are, in a very real sense, intricate expressions of the cosmic arrow of time, living proof of the universe's ongoing journey from its ordered inflationary beginning toward an ultimate state of maximum disorder and heat death. Without that singular, low-entropy start crafted by inflation, time would have no consistent direction, and the coherent history of a cosmos like ours would be impossible. The echo of that first fraction of a second reverberates through every moment of our lives, defining the relentless and irreversible flow of time itself. But as we grapple with the way inflation magnified tiny quantum jitters into the seeds for galaxies, we are forced to consider a much more dramatic and extreme possibility. What if some of those initial fluctuations weren't just tiny overdensities, but were instead so incredibly intense and sharp that they collapsed under their own gravity immediately, right there in the first moments after inflation ended? This leads us to the captivating mystery of primordial black holes and their potential role as the universe's hidden, heavyweight dark matter. The standard story of black hole formation is one of stellar death, a massive star collapsing at the end of its life, its core compressing into a point of infinite density. But primordial black holes are a completely different breed. They wouldn't need stars at all. They could have been forged directly from the raw chaos of the early universe, from those regions where the density was so exceptionally high that space itself just gave way and pinched off. Imagine the universe just after reheating, a seething, hot soup of fundamental particles. In most places, the density was nearly uniform, but thanks to those stretched quantum fluctuations, there were patches that were significantly denser than the average. If the contrast was strong enough, if a region was, say, 50% denser than its surroundings, the immense pressure of the expanding universe wouldn't be enough to stop it. That patch would stop expanding with the rest of the cosmos, slow down, and then violently collapse in on itself, forming a black hole in less time than it takes to blink. The key point is that this could happen long before the first stars were even a glimmer of an idea in the universe's first second of existence. Theoretical models suggest these primordial black holes could have formed with a stunning range of masses, dictated by the size of the original fluctuation that created them. The mass would essentially be the amount of energy contained within that overdense region at the moment it collapsed. A black hole formed when the universe was just 1 second old could have a mass comparable to a small asteroid, while one born much earlier could be as light as a tiny speck of dust, yet still possess the terrifying gravitational grip of a black hole. This is where the connection to dark matter becomes so compelling. For decades, the leading candidate for dark matter has been some kind of exotic, undiscovered particle, a WIMP or an action that barely interacts with normal matter. But what if the solution isn't a new particle, but an ancient gravitational ghost? If a vast number of these primordial black holes were created in the early universe, and if they were distributed in just the right way, they could collectively provide the gravitational scaffolding that holds galaxies together and binds clusters, all while being completely invisible to our telescopes. They wouldn't emit light, they would simply exert their gravitational pull, exactly as we observe dark matter to do. This idea elegantly sidesteps the decades-long, and so far unsuccessful, hunt for dark matter particles in underground labs. The mystery wouldn't be a new form of matter, but a vast population of frozen, cosmic fossils left over from the universe's explosive birth. However, turning this elegant idea into a confirmed reality is fraught with challenges and observational constraints. The universe, it turns out, is very good at telling us what cannot be true. If there were a large population of primordial black holes within a certain mass range, their gravitational influence would leave detectable imprints, and for many mass ranges we simply don't see those imprints. For instance, if a significant portion of dark matter were made of black holes with masses similar to large asteroids, they would act as gravitational lenses. As they passed in front of distant stars, they would briefly magnify their light in a very specific way, an effect known as microlensing. Extensive surveys, like those conducted by the OGLE and HSC collaborations, have monitored millions of stars for years. They have found some lensing events, but nowhere near enough to account for all the dark matter in our galaxy. This effectively rules out a universe where dark matter is predominantly made of black holes in the mass range of a planet to about 1,000 solar masses. Similarly, the delicate process of Big Bang nucleosynthesis, which created the first light elements, would be disrupted if too many black holes were around at that time, altering the cosmic abundances of hydrogen and helium that we so precisely observe. The collective weight of these null results has painted the primordial black hole landscape into a few narrow, but still viable, windows. The most exciting of these windows lies at the extremes, either very, very small or astonishingly large. On the low mass end, we have black holes with masses comparable to a large mountain, but compressed into a size smaller than an atom. These would be so tiny that they would evaporate over the age of the universe due to a quantum effect known as Hawking radiation. If they were light enough, they would be exploding right now, releasing a burst of gamma rays that we could potentially detect. We haven't seen the telltale signature of these explosions in the background gamma ray sky, which places a limit on how many could exist. On the other end of the spectrum, there is the possibility of massive primordial black holes weighing millions of solar masses. These could serve as the seeds for the supermassive black holes we find at the centers of galaxies, including our own Milky Way. How such behemoths could form so quickly is a major puzzle, but it's not impossible. There is even a speculative but fascinating window for planet-mass primordial black holes. If they were abundant, they could be drifting through our solar system right now, completely undetected. Their passage could subtly perturb the orbits of planets or leave trails in the vast sheets of our solar system's Oort cloud. Future experiments like the Laser Interferometer Space Antenna LISA, which will listen for gravitational waves, could be the key to uncovering this hidden population. The mergers of these ancient black holes would create a stochastic hum of gravitational waves, a background chorus of whispers from the dawn of time that would be unmistakable. The fate of primordial black holes remains one of the most tantalizing what-if scenarios in cosmology, a reminder that the answers to our biggest questions might not lie in undiscovered particles, but in the violent gravitational scars left on the universe from its very first breath. And this brings us face to face with a fundamental and humbling limitation in our quest to understand the universe's birth. We are, in a very real sense, cosmic detectives trying to solve a crime that occurred in a locked room, a room that has since been expanded to the size of the entire observable cosmos. The central challenge is one of energy. The physics that govern the cosmic inflation era operated at energy scales that are almost comically, unimaginably vast, trillions upon trillions of times higher than the most powerful collisions we can create here on Earth with our greatest tool, the Large Hadron Collider. Think of it this way: if probing the Higgs boson at the LHC is like carefully dissecting a single grain of sand to understand its structure, then trying to directly observe the conditions of inflation would be like trying to recreate the entire planet Earth, with all its oceans, mountains, and complex geology inside that same tiny grain. It's not just a matter of building a bigger machine, it's a fundamental gulf dictated by the very laws of physics we are trying to uncover. This energy frontier is so extreme that it represents a permanent barrier to direct experimental replication. We will never, ever build a collider that can reach back and literally watch inflation happen. This forces a complete paradigm shift in our approach. We must abandon the idea of direct observation and instead become masters of indirect evidence, learning to read the faint, ancient echoes that this primordial event left imprinted on the universe. So, if we can't see the event itself, what can we see? We are left with the cosmic crime scene, and our primary evidence is the afterglow of the Big Bang itself, the cosmic microwave background radiation. This fossilized light, which fills every cubic centimeter of space, is our most powerful time machine. It's a snapshot of the universe when it was just 380,000 years old, and encoded within its subtle temperature variations are the fingerprints of everything that came before, including inflation. The minute-hot and cold spots in this background are the magnified quantum fluctuations from the inflationary era, and by mapping their statistics, their size, distribution, and correlation with exquisite precision, we can perform a kind of cosmic autopsy. We can test whether their properties match the specific predictions of different inflationary models. Did they have the right level of scale invariance? Are they truly Gaussian, or are there hints of the more complex interactions that non-Gaussianity would reveal? The polarization patterns in this light, particularly the elusive B modes, are a direct hunt for the primordial gravitational waves, the ripples in spacetime that are the smoking gun of inflation's violent expansion. This is not a direct observation of inflation. It's the observation of its grandchild, the inherited trait that allows us to infer the existence and properties of its ancestor. Every new, more detailed map of the CMB, from satellites like Planck and future observatories, is like getting a higher resolution image of this ancient fossil, allowing us to see finer and finer details that can confirm or refute our most cherished theoretical ideas. But the CMB is not our only clue. The large-scale structure of the universe itself, the immense cosmic web of galaxies, clusters, and vast, empty voids serves as a second, independent witness. This sprawling architecture didn't form randomly. It grew gravitationally from those same initial seeds planted by inflation. By conducting massive galaxy surveys that map the three-dimensional positions of millions of galaxies across vast distances, we are essentially creating a 3D census of the universe's structure. The statistical distribution of these galaxies, how they cluster together on different scales, holds an encoded history of the primordial density fluctuations. It's like studying the pattern of cracks in a dried-up lakebed to understand the precise mixture of clay and silt that was there before the water evaporated. The cosmic web is a later generation imprint of the initial conditions. By comparing the patterns we see in the CMB with the patterns we see in the galaxy distribution, we can check for consistency and look for any subtle evolutionary effects that might tell us more about the nature of the initial seeds. This multi-pronged approach, using both the oldest light and the modern structure it spawned, gives us two separate lines of evidence to corroborate our story. This detective work, however, is incredibly vulnerable to contamination and foreground noise. The signals we are looking for are astonishingly faint. The B-mode polarization signal from primordial gravitational waves, for instance, is thousands of times weaker than the temperature variations in the CMB, and it's buried under a fog of polarized emission from dust within our own Milky Way galaxy. Teasing out the true cosmological signal requires not just incredibly sensitive telescopes, often placed in the pristine, dry environment of the South Pole or high in the Chilean Andes, but also multiple observations across different frequencies of light to meticulously subtract this galactic pollution. It's a painstaking process of looking for a whisper in the middle of a hurricane. The history of this search is littered with false alarms and premature announcements, where a signal thought to be from the dawn of time turned out to be just local dust. This constant battle against systematic errors keeps cosmologists rigorously honest, forcing a culture of skepticism and cross-checking that is both frustrating and essential for real progress. The very difficulty of the measurement is what makes a potential future detection so powerful and transformative. Ultimately, this challenge of direct observation shapes the entire philosophy of modern cosmology. It forces us to accept that some of the most fundamental truths about our universe may forever remain in the realm of indirect inference. We may never have a photograph of the inflated field. We may only have an overwhelming, consistent, and cross-correlated body of circumstantial evidence that points inexorably to its existence and properties. This is not unlike a courtroom where a conviction is secured not by an eyewitness, but by a mountain of forensic evidence, fingerprints, DNA, and motive, that all points to a single, inescapable conclusion. Our confidence in inflation or any theory of the very early universe will not come from a single eureka moment of direct observation, but from the gradual accumulation of data from independent sources that all tell the same story. The pattern in the CMB will match the pattern in the large-scale structure. The limits on non-Gaussianity will rule out whole classes of competing theories, and the eventual detection or confirmed absence of primordial gravitational waves will close the case on inflation's specific energy scale. We are building a case piece by intricate piece, and the jury is the entire scientific community, scrutinizing every finding with intense rigor. This is the hard, slow, and yet profoundly beautiful work of uncovering our origins, not by traveling back in time, but by learning to read the permanent record the universe left behind for us. Yet, after navigating these 20 profound mysteries, from quantum gravity to the arrow of time, we are inevitably steered toward the most fundamental and humbling question of all, a puzzle that lies at the absolute boundary of science and philosophy. This is the why anything at all question. We have an incredibly detailed and successful theory that explains how our universe came to be the way it is. Cosmic inflation describes the mechanism that took a microscopic patch and ballooned it into a vast, flat, and structured cosmos. But it is utterly silent on the deeper, more astonishing issue of why that process was set into motion in the first place. Why did the pre-inflationary universe possess the precisely tuned properties that allowed for an inflated field to exist, to enter a false vacuum state, and to then decay in such an exquisitely perfect manner that it produced a universe capable of hosting galaxies, stars, planets, and conscious life? Inflation tells us a magnificent story about the first moments of existence, but it begins its tale with a universe that is already poised to burst forth. It doesn't, and perhaps cannot, tell us why there was a universe there at all, ready and waiting to inflate. This question pushes us past the realm of physical causation and into the domain of metaphysics. We can trace the chain of events back to a tiny fraction of a second after the beginning, but then our equations hit a wall. The initial singularity, if it existed, represents a point where all known laws of physics break down. It's not simply that we don't know what happened, it's that the concepts of before, cause, and why may cease to have any meaning. Some physicists and philosophers suggest that asking what came before the Big Bang is as nonsensical as asking what is north of the North Pole. In this view, time itself originated with the universe, so there is no before in which a cause could have operated. the universe in its entirety may be a brute fact, it just is, with no further explanation required or possible. This perspective, while logically consistent for some, feels deeply unsatisfying to the human spirit, which is wired to seek reasons and origins for everything it encounters. The sheer improbability that a cosmos of such staggering complexity and fine-tuned laws would simply be from nothing seems to demand some form of explanation. One compelling scientific avenue that attempts to address this is the concept of the universe emerging from nothing through a quantum fluctuation. In this scenario, nothing doesn't mean empty space, but a true absence of space, time, and matter, a state more akin to the vacuum of quantum field theory, which is seething with potential. According to the principles of quantum mechanics, such a system can undergo a spontaneous fluctuation, temporarily borrowing energy to create a pair of virtual particles. On a cosmic scale, perhaps the entire universe is the result of the ultimate quantum fluctuation, a random, uncaused event that popped into existence from a primordial nothingness. In this picture, the universe is its own cause, a self-contained loop where the total energy, when you account for the positive energy of matter and the negative energy of gravity, sums precisely to zero. We would therefore have a universe for free, arising from nothing and requiring no external creator or first cause. This idea is mathematically elegant, but it still relies on the pre-existence of the quantum laws that permit such a fluctuation. It answers how from nothing, but not why are there quantum laws that allow something from nothing. This leads us directly to the staggering implications of the multiverse hypothesis we explored earlier. If eternal inflation is correct, then our universe is not a unique, one-off event, but one bubble in an infinite, ever-expanding meta-universe. In this context, the why anything question undergoes a dramatic shift. It is no longer about why our specific universe exists, but why the overarching multiverse exists. The answer might be that the multiverse is eternal and necessary. It simply has always been, and always will be, inflating and spawning new bubbles. In this grander scheme, the question of why our bubble has the properties it does is answered by the anthropic principle. We can only observe a universe compatible with our existence. The profound mystery of why the laws of physics are so life-permitting is then transformed into a statistical certainty. In an infinite array of universes, every possible set of laws is realized somewhere. While this elegantly solves the problem of fine-tuning for our local patch, it once again pushes the ultimate why back one step further. Why does the multiverse, with its capacity for eternal inflation and its specific mathematical structure, exist at all? The multiverse may explain the properties of our home, but it does not explain the existence of the cosmic neighborhood itself. Ultimately, this mystery brings us to the limits of human comprehension. Our brains evolved to understand cause and effect within a framework of space and time. We are masters of asking how things work within the universe, but the question of why the universe itself exists may be a category error. A question that our current tools of logic and science are fundamentally unequipped to answer. It is the final and perhaps permanent frontier of our curiosity. The quest to understand cosmic inflation has taken us on an extraordinary journey to the edge of time, revealing a story of unimaginable power and precision. Yet, in its final act, it leaves us standing before the ultimate veil, humbly acknowledging that the greatest mystery may not be the intricate workings of the cosmos, but the profound and silent fact of its very being. This is not an end to our inquiry, but a recognition of the boundless wonder that drives it, a reminder that the universe's greatest gift to us is not just the answers we find, but the endless, beautiful questions it inspires. Now, as we peer deeper into the quantum gravity conundrum, we encounter an idea so revolutionary it seems to tear at the very fabric of reality as we know it. This is the holographic principle, and its potential connection to inflation is one of the most mind-bending speculations in all of theoretical physics. The principle itself sounds like science fiction. It proposes that all the information needed to describe everything within a three-dimensional volume of space, every star, every planet, every person, every event, can be completely and perfectly encoded on a two-dimensional surface that surrounds it, like a cosmic movie being projected from a giant surrounding screen. Think of the security hologram on your credit card. It's a flat, two-dimensional surface, but it creates the illusion of a three-dimensional image floating in space. The holographic principle suggests that our entire universe, with its rich depth and volume, might be a similar kind of projection. The information that makes up your body, your memories, and the world around you isn't truly stored within the space you occupy. It's painted on the distant, two-dimensional boundary of your observable universe. This isn't just a quirky analogy. It's a serious proposal that emerges from the physics of black holes and our attempts to reconcile gravity with quantum mechanics, suggesting that the fundamental units of reality are not points in space but bits of information. So how could this possibly connect to the cosmic inflation era? The link is forged in the fires of the information paradox we just explored. Remember the puzzle of how a universe of nearly infinite complexity could have emerged from a subatomic speck. The holographic principle provides a breathtakingly elegant potential solution. That initial microscopic patch before inflation didn't need to contain all the information for the future cosmos in its volume. It only needed to hold it on its two-dimensional boundary. The amount of information a system can contain is limited by the area of its surrounding surface, not by its volume. This means the informational price tag for creating a universe is far lower than we ever imagined. The process of inflation, then, wasn't about magically creating new information out of nothing. It was an astronomical zoom function, an unimaginable magnification of a holographic blueprint that was already present. The rapid expansion took the information densely encoded on the boundary of that tiny patch and unfolded it, pixel by pixel, into the magnificent three-dimensional cosmos we inhabit today. In this view, the galaxies and cosmic web we see are not the primary reality, but a grand projected display. The true, fundamental description of our universe resides on a distant, spherical surface at the edge of space and time. This perspective radically reshapes our understanding of the universe's genesis. It suggests that space-time itself, the very stage upon which the drama of the cosmos plays out, is not a fundamental entity. Instead, it might be an emergent property, a collective phenomenon that arises from the complex entanglement of trillions upon trillions of these fundamental information bits on the boundary. The smooth, continuous space we experience would be akin to the smooth surface of water, which emerges from the chaotic interactions of countless individual molecules. This provides a stunning new angle on how inflation could have begun. The ignition of exponential expansion might not have been the rolling of a field in a pre-existing space, but a phase transition in the way this underlying information network became entangled and projected, causing the emergent property we call space to suddenly and violently unfurl. The holographic principle, therefore, doesn't just solve the information problem. It offers a completely new lexicon for describing the origin of everything, framing the birth of the cosmos not as an explosion in space, but as the awakening of a cosmic hologram. Exploring this further leads us to a profound connection with one of our other great mysteries, the arrow of time. In the standard view, the low gravitational entropy of the early universe is a baffling initial condition. But in the holographic framework, this smoothness might be a natural consequence of the universe's origins as a simple, two-dimensional data structure. A smooth boundary has less information and is therefore simpler and more ordered than a complex, wrinkled one. As the hologram was projected and the universe inflated, this initial simplicity was translated into the low-entropy, uniform state we see in the cosmic microwave background. The subsequent increase in entropy, the driving force behind the arrow of time, would then correspond to the gradual complexification of this holographic data as gravity went to work, clumping matter and weaving the cosmic web. The entire history of the universe, from its ordered beginning to its increasingly disordered future, could be the story of a hologram evolving from a simple to a complex state. Of course, this is all wildly speculative, standing at the very frontier of theoretical physics. The mathematics involved is formidably complex, rooted in string theory and the anti-de Sitter/conformal field theory correspondence, a rare and precious window into a fully realized quantum theory of gravity. Translating these abstract concepts into testable predictions for our own universe, which is expanding and not static like the models used in these calculations, is a monumental challenge. Yet the potential payoff is unimaginable. If the holographic principle is correct, it would mean that the search for the fundamental theory of everything is not a search for the particles and fields within space, but for the code, the ones and zeros written on the boundary of reality. The cosmic inflation era would be remembered not as the beginning, but as the moment the projector was switched on, illuminating the void with the glorious, three-dimensional illusion of a universe, and setting in motion the very story that allows us to ponder its existence. This journey through the deepest mysteries of the cosmos has brought us repeatedly to a stark realization. The physics of the cosmic inflation era operated at energy scales so phenomenally high that our current standard model of particle physics is simply not equipped to describe it. The standard model is a triumph of human ingenuity, beautifully explaining the particles and forces that make up our world, but it is silent on the nature of gravity and offers no candidate for the inflated field itself. To cross this frontier, we must venture into the realm of speculative, breathtakingly ambitious theories that aim to unify all the forces of nature. Two of the most prominent contenders in this quest are supersymmetry and string theory, and they offer fascinating, if unproven, frameworks for understanding the universe's very first moment. Let's begin with supersymmetry, often affectionately called SUSY. This elegant theory proposes a profound and deeply hidden symmetry in nature, a kind of cosmic partnership between the two fundamental classes of particles, fermions, which are the building blocks of matter like quarks and electrons, and bosons, which are the force carriers like photons and gluons. Supersymmetry suggests that for every known fermion, there exists a supersymmetric boson partner, and for every known boson, a fermion partner. So, an electron would have a hypothetical partner called a selectron, a photon would have a photino, and so on. This isn't just a mathematical curiosity, it solves several nagging problems in physics at once. For instance, it provides a natural candidate for the mysterious dark matter that permeates the cosmos. The lightest of these new supersymmetric particles could be stable, invisible, and abundant, exactly fitting the bill. But for our story, its most crucial role is in providing a perfect, natural home for the inflated field. In many supersymmetric models, the inflaton emerges not as an ad hoc invention, but as a necessary component of the theory, often as one of these new superpartners. The immense advantage here is that the properties of this supersymmetric inflated field are not arbitrary. They are constrained by the tight mathematical structure of the theory itself. This helps address the fine-tuning problem we encountered earlier. The potential energy landscape of the inflated field, which needed to be so unnaturally flat to drive a long-lasting inflation, can be stabilized and protected from violent quantum corrections by the gentle hand of supersymmetry. It's as if the theory provides a built-in regulatory mechanism that keeps the inflaton's hills smooth and gentle, making the beautiful universe we see not a miraculous accident, but a natural prediction of a more symmetric reality. Yet, for all its theoretical elegance, supersymmetry remains a ghost. Despite decades of searching at the world's most powerful particle colliders, including the Large Hadron Collider, not a single one of these superpartners has been detected. Their continued absence is a significant puzzle. It's possible they exist at energy scales just beyond our current reach, or that they reveal themselves in ways we haven't yet thought to look for. But the non-discovery so far means that while supersymmetry provides a beautiful and compelling framework for inflation, it is a framework built on pillars we have not yet found. It elevates the mystery of the inflaton from "what is it" to "where is the entire hidden sector of reality it belongs to?" This is where string theory makes its grand and even more radical entrance. If supersymmetry proposes new particles, string theory proposes a complete overhaul of what we consider a particle to be. It suggests that the fundamental constituents of the universe are not point-like dots, but unimaginably tiny, vibrating strings or membranes. The different vibrational patterns of these strings, like the distinct notes played on a violin string, give rise to all the different particles we see. An electron is one particular note, a quark is another. This single, powerful idea naturally incorporates gravity, with the graviton, the hypothetical particle of gravity, arising as another vibrational mode of the string. For inflation, string theory offers a vast and intricate landscape of possibilities. The inflaton field is no longer just a field in empty space. It can be associated with the position of a string, the size and shape of the extra dimensions the theory requires, or the motion of Brain's higher dimensional objects within this framework. This provides a wealth of potential mechanisms for driving inflation. One of the most famous is brane inflation, where our universe is a three-dimensional brane, and inflation is caused by the slow, attractive motion of this brane toward another parallel brane in a higher dimensional bulk. The moment of collision becomes the hot Big Bang. In this picture, the entire cosmic inflation saga is just a shadow of a much larger, higher dimensional drama. The sheer imaginative power of string theory is intoxicating, but it comes with a price, immense complexity, and a stunning lack of experimental verification. The theory predicts not one unique universe, but a colossal landscape of perhaps 10 to the 500 possible vacuum states, each with its own laws of physics and constants of nature. Our universe, with its specific inflaton properties and its life-permitting constants, would be just one tiny valley in this vast cosmic landscape. This connects directly to the multiverse idea, offering a physical mechanism for eternal inflation and the proliferation of bubble universes. Yet, this very strength is also its greatest weakness from a scientific perspective. When a theory can potentially describe almost any outcome, it becomes incredibly difficult to test and falsify. The energy scales at which strings themselves become visible are trillions of times beyond the reach of any conceivable particle accelerator. So, how can we ever know if it's true? The hope lies once again in cosmology. String theory and its close cousin, supergravity, make specific predictions about the type of inflation that could have occurred and the detailed signatures it would have left in the primordial gravitational waves and the non-Gaussianities in the cosmic microwave background. Finding a specific, intricate pattern in this ancient light could be the first indirect evidence that the fundamental fabric of reality is indeed woven from vibrating strings. Ultimately, the role of supersymmetry and string theory in the story of inflation is a tale of breathtaking ambition meeting formidable challenges. They represent humanity's most determined effort to push beyond the known, to build a theoretical bridge from the world we see to the physics of the very first instant. They provide a language to talk about the inflaton and a framework to understand how such a bizarre period could have been triggered by the fundamental laws of nature. Yet, they also remind us that we are operating in a domain of profound mystery, where our most brilliant ideas still float in a sea of uncertainty, waiting for a single, decisive observation from the cosmos to anchor them to reality. They are not the final answer, but they are the essential, daring maps we are drawing for the next great voyage of discovery. And so we arrive at a profound coincidence that lies at the very heart of our own existence. We live in a universe made almost entirely of matter. Everything we see, the planets, the stars, every galaxy, is constructed from it. but according to our best theories of particle physics, the Big Bang should have created matter and antimatter in perfectly equal amounts. For every quark produced, there should have been an antiquark. For every electron, a positron. When a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy. So, if the early universe had been perfectly symmetric, all of those pairs should have mutually destroyed one another, leaving behind a cosmos filled with nothing but radiation, a silent, featureless expanse with no atoms, no chemistry, and certainly no life. The simple, staggering fact that we are here means this didn't happen. Somehow, for every billion pairs of matter and antimatter that annihilated in the early cosmos, a single, solitary particle of matter was left over. That one in a billion asymmetry is the entire reason anything substantial exists at all. The great mystery is what caused this tiny but crucial imbalance, and the answer may be deeply entwined with the cosmic inflation era itself, suggesting that the same primordial forces that shaped the cosmos also bestowed upon it the gift of substance. This puzzle is known as baryogenesis, the genesis of the baryonic matter that makes up our world. To create a matter-dominated universe, three specific conditions, known as the Sakharov conditions, must be met. First, there must be a process that violates the conservation of baryon number essentially, a rule-breaking reaction that can produce more matter than antimatter. Second, the fundamental interactions of particles must treat matter and antimatter slightly differently, a phenomenon known as CP violation. And third, these processes must occur out of thermal equilibrium, meaning they happen while the universe is changing so rapidly that the system can't quickly snap back to a balanced state. The incredible violence and rapid transformation of the inflationary epoch and its immediate aftermath provide a perfect, and perhaps unique, stage for all three of these conditions to be met simultaneously. The decay of the inflated field during the period of reheating, which filled the universe with the hot soup of particles, was an intensely out-of-equilibrium event. This sudden, violent transfer of energy created a non-thermal environment, a cosmic crucible where the usual rules of equilibrium could be broken. If the inflated field coupled to other fields in a way that inherently favored matter, if its decay products respected the other two Sakharov conditions, then this singular moment could have been the ultimate factory, producing that one in a billion surplus of matter that everything else is built upon. Consider the sheer power of this mechanism. The inflated field, having driven the expansion of the universe, held an immense amount of energy. When it began to oscillate and decay, it didn't just release a bland, symmetric plasma. If its interactions with other particles contained even a tiny amount of CP violation, its decay could have been biased. Imagine a slot machine that, by its very design, pays out slightly more cherries than lemons over a vast number of pulls. The decay of the inflaton was like pulling the cosmic lever a near infinite number of times, and that slight statistical bias, amplified across the entire universe, could have yielded the net excess of quarks over antiquarks that went on to form every proton and neutron in existence. In this scenario, the origin of galaxies and stars is directly linked to a microscopic preference written into the laws of physics and enacted during the universe's violent rebirth from inflation. The matter we are made of isn't just a random leftover. It is the signature of an asymmetric process that occurred at the highest energy scales imaginable, a fossil from the moment the inflated field relinquished its hold on the cosmos. This elegant idea, however, is not the only possibility. Another compelling theory suggests that the asymmetry was actually generated during the inflationary expansion itself. The rapid stretching of spacetime would have excited quantum fields, potentially producing heavy, hypothetical particles right out of the vacuum. These particles, known as GUT-scale bosons because they appear in grand unified theories, could have decayed in a matter-biased way as they were created. The exponential expansion would then separate these decaying particles, preventing the matter and antimatter products from finding each other and annihilating, effectively freezing the newly created asymmetry into the fabric of the universe. It's a process that turns the entire cosmos into a vast fossil record of quantum decisions made during its most explosive growth spurt. The challenge, as with so much of early universe cosmology, is testing these ideas. The energy scales involved are far beyond the reach of any particle accelerator. Our primary evidence is the universe itself, the simple, undeniable fact that we are here, made of matter, looking out at a matter-dominated cosmos. This very existence is the data point that drives the theory. The profound implication is that the cosmic inflation era may have been a dual-purpose event. It not only solved the classic problems of the Big Bang, making the universe large, flat, and uniform, but it also may have performed the ultimate act of alchemy, transforming energy into a lopsided reality where matter could persist and eventually coalesce into the complex structures that would, billions of years later, come to ponder their own origins. Across the globe and even in the vacuum of space, a new generation of cosmic detectives is preparing for the ultimate investigation, armed with instruments of almost unimaginable sensitivity. These aren't just incremental upgrades, they are revolutionary observatories designed to listen for the faintest whispers from the dawn of time, pushing our technological capabilities to their absolute limits. The primary target remains the cosmic microwave background, but this time the focus is sharper than ever before. We've mapped its temperature fluctuations with stunning detail. Now the final frontier is its polarization. Specifically, the hunt is for that elusive, swirling B-mode pattern, the unique fingerprint of primordial gravitational waves. Finding it would be the crowning achievement of inflationary cosmology, a direct detection of the universe's first vibrations. But its continued absence would be equally revolutionary, forcing us to abandon the simplest models of inflation and compelling a radical rethinking of how it all began. We stand at a precipice where the next decade of observations could either confirm our most profound cosmic story or send us back to the drawing board. Leading this charge from the ground is the Simons Observatory, a formidable collaboration now under construction in the high, dry, and pristine atmosphere of the Chilean Andes. This isn't a single telescope, but a suite of them working in concert like a synchronized orchestra. Its location at an altitude of 17,000 feet is crucial, placing it above much of the water vapor in Earth's atmosphere that can blur the subtle signals from the CMB. The project will deploy several small aperture telescopes, which are masters of surveying large swaths of the sky to capture the grand, large-scale patterns of polarization. Alongside them will be a large aperture telescope designed for deep, high-resolution observations of smaller patches, teasing out the finest details. Together, they will measure the CMB across multiple frequencies with a sensitivity that dwarfs all previous ground-based efforts. This multi-frequency approach is the key to defeating the most persistent adversary in this search, galactic dust. Dust grains within our own Milky Way can also polarize light, creating a foreground fog that mimics the very signal cosmologists are desperate to find. By observing at different wavelengths, the Simons Observatory can meticulously map and subtract this galactic pollution, leaving behind, we hope, the pristine cosmological signal. The project's goal is to improve the sensitivity to primordial gravitational waves by an order of magnitude, either finally capturing their signature or placing such stringent limits that many popular inflationary models would be ruled out forever. But the atmosphere, no matter how thin, is still a barrier. To achieve the ultimate precision, we must go to space. That is the ambitious mission of LightBird, the light satellite for the study of B-mode polarization and inflation from dust. Planned for launch in the late 2020s, this Japanese-led space observatory will operate from the second Lagrange point, a stable gravitational spot 1 million miles from Earth, far from our planet's atmospheric and thermal interference. LightBird mission is breathtaking in its scope and specificity. To to map the entire sky in polarization with a sensitivity and accuracy that is simply impossible from the ground. It will carry an array of superconducting detectors, cooled to a fraction of a degree above absolute zero, that are exquisitely tuned to measure the faint temperature and polarization of the CMB. Its primary objective is to achieve a definitive measurement of the tensor-to-scalar ratio, the single number that quantifies the amplitude of primordial gravitational waves relative to the density fluctuations. A clear detection by Lightbird would tell us the energy scale at which inflation occurred, catapulting our understanding from a qualitative story to a quantitative physical reality. It would reveal the true strength of the gravitational waves that shook the fabric of spacetime, directly probing physics at energies 1 trillion times higher than the Large Hadron Collider can ever reach. The pursuit doesn't end with light. A parallel revolution is unfolding in the realm of gravitational wave astronomy itself. While current observatories like LIGO and Virgo listen for the collisions of black holes and neutron stars, the future lies with space-based detectors like the Laser Interferometer Space Antenna, or LISA. Scheduled for the 2030, LISA will consist of 3 spacecraft flying in a vast triangular formation, with laser beams shining between them over millions of kilometers. This gigantic instrument will be sensitive to gravitational waves at much lower frequencies than ground-based detectors. While it won't detect the primordial waves from inflation directly, those are far too faint and long in wavelength, it could observe a secondary, equally profound signal, the cosmic gravitational wave background from the early universe. This background hum could be generated by a phase transition that occurred after inflation, or by a network of cosmic strings, hypothetical one-dimensional defects that may have formed as the universe cooled. Detecting this background with LISA would provide a completely independent window into the ultra-high-energy physics of the early cosmos, complementing the CMB observations and painting a more complete picture of our origins. Beyond these flagship missions, a host of other powerful experiments are joining the hunt. The CMB S4 project, planning a next-generation ground-based telescope at the South Pole and in Chile, aims to deploy hundreds of thousands of detectors to achieve yet another leap in sensitivity. In the radio spectrum, astronomers are using telescopes to search for a subtle effect that primordial waves would have on the distribution of hydrogen atoms in the early universe. And even particle physicists are in on the act, as models of inflation often predict new particles that could, in theory, be glimpsed in the debris of collisions at future, more powerful colliders. This multi-pronged assault, using every tool at our disposal, reflects the immense importance of the question. We are not relying on a single, fragile hope, but building a robust, interconnected web of evidence that will either support the inflationary paradigm or guide us toward a new one. Ultimately, what is at stake is nothing less than our understanding of existence. The data collected by the Simons Observatory, Lightbird, LISA, and their successors will do more than just test inflation. It will rigorously probe the very nature of gravity, the unification of fundamental forces, and the validity of quantum mechanics at the most extreme scales. A confirmed detection of primordial B-modes would be a landmark moment in human history, comparable to the discovery of the CMB itself. It would provide the strongest possible evidence that we are on the right track, that our mathematical descriptions of the universe's birth, while still incomplete, capture a profound truth about reality. It would solidify the connection between the quantum world and the cosmos, showing that the largest structures indeed grew from the smallest fluctuations. Conversely, if these next-generation experiments find only silence, if the primordial gravitational wave background remains stubbornly absent, it would be a thrilling disruption. It would force cosmologists to confront the possibility that inflation is wrong, or that it unfolded in a far more complex way than our simplest models suggest. We might be driven toward cyclic universes, ekpyrotic scenarios, or ideas we haven't yet conceived. This is the true engine of science, not the comfort of confirmation, but the exhilarating possibility of being proven wrong, of having our deepest assumptions challenged, and being compelled to look at the cosmos with fresh, wondering eyes. The next chapter of our cosmic story is being written not in theory, but in the design of these incredible machines and the data they will soon send back to Earth. And so we have journeyed to the very edge of time and back, exploring the 25 profound mysteries that shroud the universe's very first moment. We began with the enigma of the trigger, what was the initial spark that set off the universe's runaway expansion, and was it the inflated field, a phase transition, or something far stranger? We pondered the graceful exit. How and why did this staggering growth cease so perfectly, transforming its energy into the hot particle soup of the Big Bang in an exquisitely tuned process called reheating that made our existence possible? We then joined the epic hunt for the primordial gravitational wave background, the ripples in spacetime that are the ultimate smoking gun for inflation, a whisper we strain to hear amidst the cacophony of the cosmos. We marveled at how inflation masterfully solved the horizon problem, explaining why the universe looks the same in all directions by showing us that distant regions were once intimate neighbors, and we saw how it resolved the flatness problem, acting as a cosmic iron that smoothed the universe's geometry to the perfect flatness we observe today. We witnessed the incredible link between the quantum and the cosmic, discovering how microscopic jitters were stretched to become the seeds for every galaxy, star, and planet. And we saw how inflation washed away the troublesome magnetic monopoles, cleansing our cosmic neighborhood of these predicted but missing relics. This led us to the staggering possibility of the multiverse, where our entire cosmos is just one bubble in an eternally inflating meta-reality, a concept that challenges the very meaning of a unique universe. We dared to ask what came before, confronting the initial singularity and the possibilities of a big bounce or a creation from nothing, a question that pushes our physics to its absolute breaking point. We grappled with the quantum gravity conundrum, the fundamental conflict between the theories of the very large and the very small that prevents us from fully understanding the ignition of inflation itself. We acknowledge the problem of fine-tuning, questioning whether the incredible precision required for inflation to work points to a deeper law or a cosmic accident. We then considered the compelling alternatives: the cyclic universe, the ekpyrotic scenario, and string gas cosmology, each offering a radically different vision of the beginning. We explored the haunting connection between the inflated field of the past and the dark energy accelerating our universe today, wondering if they are two faces of the same cosmic force. We delved into the cosmological information paradox, asking how our complex cosmos could have emerged from a subatomic speck, and we confronted the baffling measure problem, the challenge of making predictions in an infinite multiverse where everything happens. We examined the hunt for non-Gaussianity, the search for tiny flaws in the cosmic blueprint that could reveal the detailed physics of inflation, and we peered into the trans-Planckian problem, acknowledging that our entire story may be built upon physics from a realm we cannot yet describe. We saw how inflation may have set the arrow of time, providing the low entropy beginning that allows history to unfold, and we investigated the potential for primordial black holes to be the dark matter that shapes the cosmos. We faced the challenge of direct observation, realizing we must forever be cosmic detectives reading indirect clues from the cosmic microwave background and the large-scale structure of the universe. We stood before the ultimate question of why anything exists at all, a mystery that takes us to the boundary of science and philosophy. We explored the revolutionary holographic principle, which suggests our 3D universe is a projection from a 2D boundary, and we saw how theories like supersymmetry and string theory provide a grand, if unproven, framework for unifying these ideas. Finally, we uncovered how the same inflationary epoch may have forged the universe's matter-antimatter asymmetry, that 1 in a billion surplus that is the reason we are here at all. This brief, almost immeasurable moment, the cosmic inflation era, holds the keys to our entire cosmic origin story. It set the stage for everything that followed, from the largest galaxy clusters to the very fact that we can sit and ponder its mysteries. The pursuit of these answers is far from over. It is what drives the very frontiers of physics and cosmology, inspiring a new generation of telescopes, satellites, and brilliant minds to keep looking, keep questioning, and keep reaching for a deeper understanding of our magnificent universe. We would love to hear from you on this incredible journey. Which of these 25 mysteries captures your imagination the most? Let us know.